My voice is clear, right?
Yes, sir.
Okay.
Sir, you make Srinivas sir as a co-host.
Yes, sir.
Is it Rajadas online?
Yes, sir. Rajadas sir is also online, sir.
Yes, sir. Yes, sir. I'm doing, sir.
Sir, please make Srinivas sir as
Yes,
a
yes, sir. Yes, sir.
co-host. And Jaban Meher also you make co-host. Stephen Bayer also make co-host.
Okay, sir. I'm making you host. Then I'll be sharing, sir.
Yes, yes, okay.
You are host now.
Madam.
So, Rishi sir, you will display the pictures, no? I've sent you.
1 minute, sir. Yes, yes, yes. I'm doing, sir.
Yeah. Yeah, okay.
Good morning, Srinivas. Piyush here.
Hello.
Namaskar, namaskar.
Namaskar. How are you?
How are you?
Hi. Namaskar, Piyush ji.
Yeah. To all of you, yes. So nice that you are arranging this. You are coordinating this symposium. It's very important.
It's my pleasure. It's my pleasure. I'm really honored. Thank you for this.
Hello, Srini.
Hi, Shanta. Congratulations, Shanta.
Oh, okay, thank you. Yeah, so maybe I can plan, see if I can share the screen and.
It is showing now.
Yeah. Picture is showing.
It is showing.
No. Now it is displaying or not? Photograph of that person.
Sir, displaying.
Yeah, photograph of, yeah. There is one more photograph, right?
One more is there, sir.
Sir, 2 photographs is coming, sir.
Only one is coming. You just
No, sir, it is coming. You watch, it will become AC.
slideshow. We have to make it.
It's only one coming.
Only one is coming.
Yes.
One of two. Yes.
Yeah, this is, yeah.
Yes.
Right.
Keep the second one, sir.
Yeah. The thing is, the other one is with the Tata and Baba.
Yeah.
Who have been very, responsible for, bringing him to India. So maybe sometime that also can be displayed. I will take the name of Baba and Baba. At that time, maybe that can be displayed. Huh?
Or it can be put in the gallery.
No, madam, join. Hello.
Namaskar, Satyadev ji.
Namaste, 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 Srinivas. How are you?
Good. Chandra.
Well, I'm very happy that you undertook this job.
Well, I'm grateful to you all for honoring me with this job.
Even Professor Raghunathan mentioned very highly about Casey in his inaugural speech.
Yes.
And I hope this symposium will do some justice to his memory.
Yeah, rightly. Actually, it's our way of paying tribute to him.
It was a very good suggestion, and we immediately accepted it, thinking that actually people have somehow forgotten K. Chandrasekharan. It has been a long time since he left India,
Actually,
and there has not been any activity regarding.
Number theorists can never forget. Yeah,
Of course.
those in analytic
No, I mean,
number
what I mean is
theory,
they cannot forget, but nothing has been done in his honor. Many things have been
Ah.
done about other people, but in his honor, nothing concrete has been done. So that's what I
Yes.
was trying to say.
Yes. Right.
Shall we start?
Yes, sir.
Yeah, I think it is time. Yes.
Sir, over to Krish Chandra, sir.
No, it's for you to start the whole thing.
Okay, sir. Yes, sir. Very good morning to all of you. At the outset, I'd like to welcome all the dignitaries for this important symposium on number theory. I'd like to welcome Professor Satyadev sir and Professor Piyush Chandra sir for this symposium. I also welcome Professor Srinivas Kotyada sir for chairing this and organizing this symposium. And there are eminent speakers who are speaking on this symposium. So on behalf of the organizing committee and IMS 2020, I welcome all of you for this symposium once again. So thank you one and all. And Professor Srinivas Kotyada is an eminent mathematician. Is a professor in Indian Mathematical Sciences Institute, IMSC Chennai. And his work on number theory is greatly acknowledged worldwide. And he also visited VIT on the National Mathematics Day. We have celebrated in the year 2018. And he is the chief guest for that function. And he graced the talk by introducing the Ramanujan's work. So we have enjoyed that lecture, and he is greatly associated with VIT as well. Thank you very much, sir. And now the session is handed over to Professor Srinivas Kotyada. Thank you, sir. And it's an honor for us to be host this symposium as a part of IMS 2020. Professor Piyush Chandra sir. Yes, sir. Over to Srinivas sir.
Yeah. Thank you, Rishi sir. Thank you very much. It's my pleasure, and I'm grateful to Indian Mathematical Society for giving me this chance to convene this number theory symposium in the name of K. Chandrasekharan. So, actually, personally, I got very much benefited by Casey, as we popularly call him Casey, during my student life, and even now also because of his very nice books that he has written and the fundamental papers that he has contributed. So, and we have also had this Professor M.S. Raghunathan has spoken quite a lot about him, quite highly about him. So the audience is introduced to Casey. However, for the sake of formality, let me tell a few things about him. So Casey was born on 21 November 1920 in Guntur. It's a place in Andhra Pradesh. He studied at Residency College, Madras, and he did his PhD under Anand Rao, who was a colleague of Ramanujan, and also he was a student of Hardy, G.H. Hardy, and and therefore you can see the analytic number theory flavor in Casey's work. So his work mostly centered around analysis and number theory. Casey went to Institute of Advanced Study, Princeton in 1946. And they wrote a book with Boschner on Fourier transform there. And in the year 1948, Homi Bhabha visited Princeton. He was looking for people, for TIFR, which he had plans. And then he was recommended that Casey would be a good choice. So thus, Casey came to TIFR in 1948. He then started building the School of Mathematics. He invited eminent people. So he invited K.G. Ramanathan, for example, in the beginning. And then together, they started the graduate program at TIFR, which is one of the best in our country. And he invited world-class mathematicians. He invited world-class mathematicians like Carl Ludwig Siegel, Eilenberg, Rademacher, Maas, Eichler, Jareski, Lawrence Schwarz, and Atlas Elberg, for example, who spent considerable amount of time in TIFR, which has benefited the faculty at TIFR and in general the mathematics in India. Okay. Another significant contribution of Casey is so in our perspective, he was also the chief editor of Journal of Indian Mathematical Society for 8 years, and also the chief editor of Mathematical Students for 5 years. So we have had people like Casey in IMS, which is the reason why it is one of the best organizations in the world. So Casey left TIFR in 1965 to join ETH in Zurich, Switzerland, and remained there till his death. So his collaboration with Raghavan Narasimhan brought many important contributions to number theory. As I mentioned in the beginning, his work on the zeros of ideal class zeta functions, his books, for example, his works on generalizing functions which are akin to Riemann zeta function by means of functional equation. It's one of the fundamental work which everyone who is interested in analytic number theory, they must look at. He was a man of high intellectual humility and integrity, whose striving for excellence helped the School of Mathematics at TIFR gain the reputation of being a world-class center for mathematics. Okay, and his students include, for example, Seshadri and M.S. Narasimhan. So we are very blessed that it is the right occasion that we are having this ceremony in his honor. So I hope we will at least in our own way this is a kind of paying tribute to him. So I will not take much time because speakers are ready to kind of start the session. So I welcome you all for this centenary symposium in number theory. So thank you, organizers. So I think we can begin our talk session. Yes. You, sir. Am I audible?
Yes, sir, audible, sir. We can proceed.
Yeah, you are.
Yeah, so we have 5 speakers today. Professor Shanta Laishram, Professor Stephen Baer, Professor Padma, Professor Jaban, and myself. So we will start one by one. So I request Professor Shanta Laishram from ISI Delhi to start his talk. He is one of very reputed transcendental number theorists, and we are happy to have him. So, Professor Shanta, can you start sharing your screen?
Yeah, sure. Okay, thank you, Srini. Can you hear me?
Yeah,
Yes, yes.
okay.
Yeah.
नहीं कुछ लियो
So just give me 1 second. Let me try to. Hello. So okay, so is the screen big screen or is it short screen? Can you please tell me?
No, it's good. Okay, you keep start.
Okay. Okay, so first of all, I'd like to thank the organizers for this symposium, and in particular, I also thank the Srini. So for organizing this session. So today I'll be talking about this Lucas sequences and arithmetic, and I'll begin my talk here. Just I'll put the timer so that I know when to stop. So can you see my? I've changed the screen. Can you see it? Is it in the front screen or in the next page?
No, it is on the front screen.
Okay. Yeah, I think I'm using Mac sometimes. Okay. Okay.
Yeah, so it's okay. It's good actually.
Oh, okay. Thank you. So we all know about this Fibonacci sequence, which is one of the most widely studied sequence. So Fibonacci sequence, as you know, is the sequence starting at 0, 1, then the next term is the sum of previous two terms. So the first few terms of the sequence is 0, 1, 1, 2, 3, 5, 8, etc. So, but then this is a very special case of a general family of sequences called Lucas sequence. So let me now explain what is a Lucas sequence. So a binary recurrence sequence is a second order recurrence sequence given by u of n plus 2. So if you know un and un plus 1, then you know u of n plus 2. By taking u of n plus 2 is r times un plus 1 plus s times un for all n bigger than or equal to 0. So we're going to take r and s to be co-prime integers, u1 are integers. So u1 are given integers, r and s are co-prime integers. So for this for this recurrence, we have the characteristic polynomial, which is given by x square minus rx minus s is equal to which I factor as x minus alpha times x minus beta. Now, from the theory of recurrent sequences, one can easily see that if alpha is not equal to beta, then un is actually equal to a times alpha n plus b times beta power n for all n bigger than or equal to 0. Now we're going to call such sequences non-degenerate. So here a and b will depend on the sequence. So given by taking u0, u1, one can write a, b, quite easily. So we call such a sequence non-degenerate if a, b times alpha beta is non-zero and alpha by beta is not a root of unity. So we want to avoid alpha by beta being a root of unity and all of these numbers a, b, alpha, beta to be 0. We want to avoid them to be 0. So from now on, we'll only consider non-degenerate sequences. So in case of Fibonacci sequence, as I told you, so r equal to s equal to 1. The characteristic polynomial is given by x minus alpha x minus beta, where alpha and beta are the golden ratios, 1 plus root pi by 2 and 1 minus root pi by 2. And it's easy exercise to show that Fn can be written as alpha power n minus beta power n by alpha minus beta for all n bigger than or equal to 0. So this is called the closed Binet formula for Fibonacci. And with the same alpha beta, if you put alpha power n plus beta power n, then it's a integer for all n bigger than or equal to 0. So we call Ln the Lucas sequence. This is the and if you put n equal to 0, then it's L naught is 2, L1 is 1, L of n plus 2 is L of n plus 1 plus Ln for all n bigger than or equal to 0. So it satisfies the same recurrence as Fibonacci, but the starting point is different. Remember that L of 1 is alpha plus beta, which is R. So not only Fibonacci, Lucas, we can also talk to, like, given a Pell equation or Brahmagupta Pell equation, x square minus dy square equal to plus or minus 1, where d is bigger than 1. We know that this equation has infinitely many solutions. So take a fundamental solution of this Pell's equation, x square minus dy square equals plus or minus 1. So by fundamental, I mean the solution with least x1 positive and y1 non-zero. Then all the equations, all the solutions are given by this xl plus root dyl is x1 plus root dy1 for L. So there's a mistake here, xl. And we call xl the LS solution of the Pell's equation. So I want you to observe that, like, the equation x square minus dy square equal to minus 1 may not have a solution, but x square minus dy square equal to 1 always has a solution for d non-square bigger than 1. So when I take this list of these solutions, so basically I'm taking all the solutions of x square minus dy square equal to plus minus 1. And also it's an easy exercise to show that if you put zeta is x1 plus root dy1, zeta is x1 minus root dy1, then xl is zeta power l plus y zeta power l by 2. Then yl is zeta power l minus zeta power l by 2 root d. So this is an easy thing to see. So if you put x naught is 1, y naught is 0, then both xl and yl are binary difference sequences with a characteristic equation x square minus 2x1 x plus minus 1. So these are Pell solutions of Pell equations are also binary difference sequences. Now I'll define the general Lucas sequences. So given R and S co-prime integers, let u0 is 0, u1 is 1. Then a binary recurrence sequence is called a Lucas sequence of first kind with the roots first kind, and the roots alpha and beta of the characteristic equation x square minus rx minus s gives the sequence un is alpha power n minus beta power n, and bn is alpha power n plus beta power n. So here bn is called a Lucas sequence of second kind, and you can see easily that b naught is equal to 2, b1 is r, and b of n plus 2 and bn plus 2 satisfies the recurrence r times bn plus 1 plus s times bn for all n bigger than or equal to 0. So Fibonacci is the Lucas sequence of first kind, and Lucas sequence is a Lucas sequence of second kind. So it's a little bit misnomer, but when the second kind corresponding to Fibonacci is itself called Lucas sequence. The Pell sequence, the y coordinate, the xy, that y coordinate is the Lucas sequence of first kind, and x coordinate is the Lucas sequence of second kind. Just for your information, I'm just showing you, I'm refreshing those. So Lucas sequence of first kind is given by un is alpha power n minus beta power n by alpha minus beta, where u0 is 0, u1 is 1, and un plus 2 is r times un plus 1 plus s times un for all n. And Lucas sequence of second kind is given by Bn, which is B alpha power n plus beta power n for all n bigger than or equal to 0. And B naught is 2, B1 is R, Bn plus 2 is R times Bn plus 1 plus S times Bn. Of course, recall that R is alpha is the root of x square minus R x minus S. So we have written the roots alpha and beta. And alpha and beta are complex conjugates when R square plus 4S is less than 0. So this is just a recap of what the binary recurrence sequences look like. So I just want to mention few of the well-known sequences. You know Fibonacci with R equal to S equal to 1 and Lucas sequence are the corresponding Lucas sequence. So when R equal to 2, S equal to 1, this is called a tail sequence where alpha is 1 plus root 2 by root 2, and beta is 1 minus root 2. And these are the first few terms of the sequence. So R is 2, S equal to 1. And Campanella tail sequence or tail Lucas sequence is given by, okay, so the other Vn where R is 2 and S equal to 1. Interestingly, all the terms of this sequence are 2 times a multiple of 2 times an odd number. So this and also one can talk about the sequences like Jacobson sequence where R is 1, S equal to 2, or Jacobson Lucas sequence which is the corresponding sequence. So by the way, interestingly, this Mercian sequence given by 2 power n minus 1 is a binary Lucas sequence with R equal to 3, S equal to minus 2. And Mercian Lucas sequence is Fn, which is 2 power n plus 1. So this is also a Lucas sequence. So at first we may not observe the 2n minus 1 is, doesn't look like a recurrent sequence, but it's a recurrent sequence with R equal to 3, S equal to minus 2. So these are some of the well-known binary recurrence sequences. So binary recurrence sequence has this interesting property that of existence of primitive divisors. So primitive divisors are the primes which like P is a primitive divisor of UN if P doesn't divide UM for every m less than n, and P doesn't divide R square plus 4S for the discriminant, then such a prime is called a primitive divisor of UN. And primitive divisors are always congruent to plus or minus 1. And similarly for Vn, you can define a primitive divisor. So one of the interesting things which we need to say is that primitive divisors are always congruent to plus or minus 1 mod n. Okay, so yeah, for example, in case of Fibonacci, this except 1, 1, 2, 8, and 144, every other term has a primitive divisor. And in case of Lucas, except 1 and 4, and 18, every other term has a primitive divisor. So this is a well-known primitive divisor theorem. So it's one of the quite important results in recurrent sequences, and it has a lot of applications in Dirac-Fontaine equations and other areas of number theory, and in fact other areas of mathematics. So we now explicitly know for which binary recurrence sequence there's a primitive divisor and for why it doesn't have a primitive divisor. So for example, when n is outside 1, 2, 3, 4, 6, it always has a primitive divisor except when n is 5, R and S are given by one of these terms, or when n is 7 and R and S are given by one of these pairs. So this is a well-known primitive divisor theorem. And actually it started, so I'm going to go a little bit fast here because I want to go to the result. Actually it started with the work of Zygmundi in 1892 and with the result of Carmichael for the Fibonacci sequence. And for the alpha beta conjugate, complex conjugate, it was quite complicated. It took a long time. And finally, only in 2000, this proof of theorem was completed. So, for example, this in f of 210, if you factor this number, so if you of course, that primitive divisor exists, but if I ask you to guess the primitive divisor, most likely you'll guess this number, this largest prime divisor, but it can have a, the primitive prime divisor need not be the largest divisor. So I just want to show you an example here. The primitive prime divisor F210 is 21211 and 767131. So largest prime divisor need not be the primitive divisor of F210. Like this prime is a primitive divisor of 105. So S2 triple S2 3 4 S1. So the interesting thing is that primitive prime divisor always exists after a certain S, after a certain N. So for Fibonacci, for n bigger than 12, it always exists, but the largest prime divisor need not be a primitive divisor. So now I want to come to this arithmetic of binary recurrent sequences. So we can ask, since this is sequence, we can ask many questions. So whether this sequence contains infinitely many primes, which we don't know how to prove. Even for Fibonacci sequence, we don't know how. We don't know if there are infinitely many primes in the sequence. So Mercian prime conjecture is a special case of this problem. And also we can ask that, are there infinitely many perfect powers in a recurrent sequence? Or are there infinitely many factorials in a binary recurrent sequence? Or are there many Catalan numbers in a binary recurrent sequence and more? So basically, any property of integers we can try to ask on these binary recurrent sequences. So today I will talk about these two problems on the factorials in Catalan numbers. Okay, so let me define PF to be the set of factorials. So it's a product of factorials plus minus a product of factorials, where this is of this M1, M2, these are non-decreasing and M1 is bigger than 1. So Lucas showed that a Diophantine equation, product of terms of a this Diophantine equation, that product of terms of a Lucas sequence being a perfect product of factorials, it has only finally many positive integer solutions, n1, n2, n3, which are effectively computable in terms of Lucas sequence. So given a Lucas sequence, this equation 1 has only finally many solutions. Unfortunately, the bound can be quite huge, and at the same time, the bound depends on this Lucas sequence. Then we want to ask some we want to find a general bound of, can you give a bound independent of the sequence? So that was the problem we started. Before that, I want to make the following remark. Let UN be given, so you look at the sequence UN given by R and S, where S is not equal to plus or minus 1. Then S doesn't divide UN for any n. So if you look at this equation, product of terms of the sequence being a product of factorial, then we know it's bound when S is not equal to plus or minus 1. It's bounded by the cardinality of S. So in particular for Mercian sequence or Jacobson sequence, life is very simple because none of the term is divisible by 2, so it has only trivial solution. The problem becomes more interesting when S is equal to plus or minus 1, where we know that for every j, there is a term divisible by j. So finding a uniform bound is an interesting problem. So in this regard, we consider the following equation. So we just take, okay, given a binary recurrent sequence, you look at the nth term and ask whether it can be written as product of factorial. So this is the following result which we proved. So nth term of a binary recurrent sequence, the Lucas sequence being a product of factorial, implies n has to be n has to be it has to only come from the numbers 2, 3, 4, 6, 8, and 12. So basically, if n is bigger than 12, there are no solutions of this equation 2. And in case of alpha and beta are real, then there are no solutions for when n is n. Here, this is a joint in a joint work earlier with Luca and Florian, Luca and Mark Sears, we proved that we actually got the bound n is less than 62,000 in the above result, which I actually reduced to this bound here in the as I stated in the theorem. So basically, we all know instead of a okay. So earlier, Luca's result was that you have a bound which depends on the sequence, but now I have a result which is completely independent of the sequence. Similarly, we got we got a result for the Lucas sequence of second kind. So you have this Bn which is product of factorial. Then here you can also get okay, except for n equal to 1, 2, or n is odd prime less than 787, there are no solutions. And when alpha and beta are real, then we get much better. So this is the result. I mean, this is quite interesting in the sense that we get a bound which is completely independent of the sequences, and we are able to say completely clearly. So here I want to all of you are familiar with ABC conjecture, so I'll skip it. So basically, it's one of the most difficult problem in number theory, where given A plus B equal to C, where ABC a pairwise coprime, then C is less than radical power 1 plus epsilon. So this is the conjecture. So what I mentioned is that in my theorem, I said that except 2, 3, 4, 6, outside 2, 3, 4, 6, 12, there are no solutions. But can you say something in this range? So in 2, 3, 4, 6, 12, can you say there are only finitely many solutions or infinitely many solutions? Regarding this, we can show that this when n is 2, 3, 4, there are only finitely many solutions. And when there are infinitely many solutions, when n is 6 and 12, there are only finitely many solutions under ABC conjecture. So without ABC conjecture, we don't know how to show that when n is 6 or 12, there are only finitely many solutions, which we expect it to be true. And so I want to sort of give you some sort of a question for the audience. So basically, we try to check for like we have a complete bound. So we check for the values r less than 100, s less than 1000, and we find that there are only few solutions which I've listed here, which you can all see. So we expect that there are no more solutions other than this. So that's what we want to conjecture. So we conjecture that when alpha and beta are real, that is when r square plus 4s is bigger than 0, then only solutions are given by n equal to 12, rs is plus minus 1, then or n equal to 6. So basically, when alpha beta are real, we expect only these few solutions we expected, which I'm showing here. So under ABC conjecture, we know there are only finitely many, but we even finiteness part we can still prove it. And another problem which I want to state is the following. So prove that if you take a product of terms of a sequence being a product of factorial, then you give a bound n naught such that each of these numbers n1, n2, nc is bounded by some n naught. There's also another open problem. So now in the last 5 minutes, I just want to I'll skip a little bit because this is about the sequence of solutions of this Pales equation. So what we are asking is that can you say something about the solutions of the Pales equation being a product of factorial? And we saw that there are only finitely many solutions, so which we could able to show completely. So maybe I'll just state a result on the Catalan numbers and stop. So for a positive integer m bigger than or equal to 1, we know that middle binomial coefficient you denote by bm. The mth Catalan number cm is given by 1 over m plus 1 times 2m choose n. This is the integer, and write gm for one of this bm or cm. That is either middle binomial coefficient or Catalan number, and you find you form the number which is the product of all these middle binomial coefficients or the Catalan numbers. This is the history which connected to the study comes, this set comes in the trying to understand this non-trivial solution system of equations which arose from n-dimensional complexes in topology. So I won't go into it. So just I want to say the following theorem and say something about the proof. So for each n, let Dm be either binomial coefficient or the Catalan number. Then un being a product of this term implies that there are no solutions outside 1, 2, 3, 4, 6, 8, 12, and 16. And further, when alpha and beta are real, you can remove 16 also. So this is also first in a joint work with Luca and Sears, we prove it for n less than when n is bigger than 6500. But I actually improve it further to this completely explicit result. And we have similar results for this Dn, the sequence Dn. And so the thing is that in the sequence Dn, we are not able to prove it completely for all primes less than 390. For all. So I just want to tell you why this is quite complicated here. So in case of this Dn, when alpha and beta are complex numbers, the life is actually a little bit more complicated. So this is what I want to sort of tell. I want to stop by saying something about the cyclotomic polynomials and bring in this linear forms in logarithm. So for the proof of this result, what we actually need is that we have to sort of bound the terms of these cyclotomic polynomials. All of you know that cyclotomic polynomial is like Cl alpha beta. Cl of alpha beta is alpha minus 2 pi e power 2 pi I k by L beta. So where k and L are co-prime. So you look at this LS cyclotomic polynomial homogenization, and what we know is that we want to look at the prime divisors of this cyclotomic polynomial. And when we want to look at the when this terms being a factorial of Catalan numbers, then you need to get a bound for this alpha power L plus minus beta power L. When alpha and beta are real, or it's quite easy. The upper bound is also quite easy. But when alpha and beta are complex numbers, the finding a bound is very complicated. So when alpha and beta are complex conjugates, if you want to find a lower bound for alpha power L plus beta power L, it becomes quite difficult. So we need to use theory of linear forms in logarithms to get a lower bound. And the way sort of is that we bring in the deep theory, which is coming from Baker's theory of linear forms, and we try to get a bound, something like so I'm going a bit fast, quite fast here. So basically, you try to bring it in the form of a linear form and use certain properties which is coming from the linear forms and get a bound which is quite complicated. And with this bounds, actually, we can get a result like this, which is log of alpha and beta complex conjugate. And when log of alpha is bigger than 4 and L bigger than or equal to 3, you get a bound like log of alpha for L plus minus beta for L is bigger than this number. So bigger than or equal to this number. So if you see when L is like less than around 5,000, less than 5,000 or so, this is a negative number. You don't get anything. So you get some bound when L is bigger than when L is large. So even linear forms doesn't help much here. So we have to do quite a bit of estimate. So I'll just, in the last few seconds, I just want to tell you that so for the proof, we have to use different ideas from prime number theory, analytic shading argument, bound for primes dividing and arithmetic progression, and computing. So quite a bit of things we have to combine and then prove it. So I don't have much time to talk about it. I'll be happy to take some questions. Thank you.
Thank you, Shanta.
Oh, yeah.
Very nice talk. So anyone has any questions to ask?
Yeah. Sorry that I went a bit fast because of the timing. So
Yeah, I know. So you can unmute. I mean, anyone who is willing to ask a question can unmute and ask. Please do that. So Shanta, some of the things that you have stated your theorems, are they
Yeah.
also valid for this balancing sequence? It's a sort of similar. Right?
yes. Yeah, definitely.
So-
Actually, balancing sequence is a part of, it's a family of Lucas sequences. So definitely they're valid.
So it holds true for all of them.
Yeah.
I see. So if there are no questions, then let me thank Professor Shanta Laishram for a wonderful talk. Thank you, Shanta.
Oh,
Thank you very
Okay,
much.
thank you very much, Srini.
Good. Now we can start the second talk. I request Stefan Bayer. Stefan, are you there?
Yeah, Stephen is asking, can you hear me? So maybe he's there, but his mic is not working.
I don't see his name actually in the.
Just in the chat, he wrote something like, "Can you hear me?" So
Yeah, but he might have logged out. He's there. He's there. Stefan, can you undo your video also? He's able to hear Abhi because he's not muted. Stefan, are you able to hear me?
So he says he
Sir,
can hear you
Srinivas, sir?
perfectly, but he is trying to change the device.
Yes, sir.
I see. Okay. Okay. I see.
The old days, we just had to bother about chalk piece or blackboard.
yeah, that's true. Hi, sorry, how are you?
Yeah, good to see you. Nice lecture. Very nice.
Okay, thank you for this.
Congratulations for your promotion. I mean, everybody is
Oh,
getting it, but
okay. Yeah, thank you. Yeah.
If he's going to take some more time, then maybe we can start the next talk.
Yeah, maybe you can ask someone to, then we can lecture.
Is it okay with you, Stefan, if we start the next talk and then you can?
So
Yeah.
now you can hear me, right?
Yeah, I can hear you. Yeah, we can.
Okay, excellent.
Good.
So then I will just
Share your screen.
I need to switch that off. So I leave that meeting and good. So I still need to get my slides. One moment.
Yeah, sure.
Okay, so I have opened my slides.
Yeah.
I will keep it short then, because we've lost some time now. Sorry for the technical problems.
Okay, no problem. No problem. So have you started sharing?
So I share the screen. So can you see?
No.
Yeah, we can't see your screen.
Yeah, so you can see the screen, yeah?
No, no,
No,
no.
we can't. We can't.
Sir, Srinivas sir.
Yeah.
Sir, actually, this Stephen sir cannot share his slides as he is not the co-host, sir. Just we called Rishikumar sir to make him as a co-host, sir. It will.
Sir, I'll do that one. Sir, 1 minute, I am doing that.
Yeah. I see. Okay. Stephen, just wait for a minute.
Yeah. Okay, no problem. Mm-hmm.
So this has to be done in every talk. You just make the speaker a co-host.
Sir, I have done, sir. I just now done.
Yeah.
Initially, I made him co-host. Maybe he left and joined. That's why he made it. Sir.
I see.
Okay, so now you can see the screen?
No.
Yes, sir. Just a minute. It may take some time, sir. Sometimes due to network, it takes few minutes, few seconds. Your name appearing because you are sharing from abroad. Are you sharing the screen now?
Yes, I'm sharing.
No, I can't see anything yet.
Yes.
Sir, Professor Rajadas.
So I'm co-host now?
Yes,
Sir,
already
he has
co-host,
to
sir.
share actually. Share option is there. Share screen option, green color. It is available at the bottom.
First, you open the PPT or the file.
Yeah, so I have opened the file.
Then you start share screen at the bottom of your
I did that already, but okay. Once more. Share. Yeah. Okay.
Green color is there. Green color.
Yeah. Yes.
There,
So
top corner, you will find out desktop's screen.
Screen. Okay, screen.
Yeah. Click on it. Then again, come to right hand side bottom. Share option will be there.
Right hand side. Moment. Allow
After selecting
permission.
that screen, you'll find out right hand side.
Right hand side.
Bottom,
can you share your screen and show, explain us?
Okay. 1 minute.
Sir, 1 minute. Rajadas will give a small how he will share. Just look into that.
I think.
1 minute, sir.
Yeah.
See, are you able to see?
Yeah, we are able to see. Stefan, are you able to see that?
After selecting the screen, what I have blue color is showing, then you have to come right hand side bottom. There is a share, right? So
Okay, I try again. Moment.
You just stop sharing, sir. Rajadas, sir, you please stop share.
So what is that? Is it now?
another option is he can email it to Professor Srinivasan, who can share it.
Or you can email it to, you can email it to me.
Yes, sir. Email it to us also, we'll share.
Yeah, or
Yeah.
Rishi
How
sir,
do I
email it
get
to
back
organization.
to moment? I need to. Okay, I forward this to you. Yeah.
Rishi sir, can you tell your email ID? He can forward it to you directly there.
Yes, sir. I'm putting in the chat box.
Yeah.
Actually, you can, Stephen, you can reply all to that email, the last email by Srini, then everyone will get it.
Okay.
Yeah.
Sir, I have just given my email ID at chat box.
Okay, so I replied to that email.
Yes, fine. I'll share.
No, that email which was sent by
Shikmar@vat.ac.in.
So. Okay, so I have sent that. Did you get that?
Just a minute, I am checking. 1 minute, I think so. Sir, I got it. I'm just downloading.
Okay, so I need to join this Zoom meeting again. There's some problem here. One moment. Okay.
All right. Okay. Now can I share?
Yes. Yeah. Please.
Yes, is it fine?
It says.
Can we request Professor Stephen to put on his video also?
Yes.
So my video is on.
No,
Can you hear me?
Yeah. Now the screen is visible. Stephen, you can put your video on for some time. Yeah.
Yes, the video is on. Hello.
Yeah, we are not able to see you. Camera is it on?
Hello. Okay.
Yes,
Good. So can you see and hear me now?
Oh yes, thank you.
Okay, great.
All right. So I sorry for the inconveniences. So now we have the second speaker of this number theory symposium by Professor Stephen Bayer, a very good friend of mine and a very big analytic number theorist, interested in C methods and things like that. So he's in Ramakrishna Mission Vivekananda Education and Research Institute, Belur. So I invite him to begin his talk.
Okay, thank you very much for inviting me. So you can hear me?
Yeah.
Okay, great. So I will keep things short because we've lost some time. So that's not a problem. I can convey what I want to say also. In
sure. Okay. Yeah.
Okay, so this topic of the talk connects with work by the previous speaker, Chandrasekharan. It's about prime powers dividing products of consecutive integer values of a certain polynomial, the polynomial x to the 2n plus 1. Okay, can we go to the next slide, please? Yeah, Thank you. So the general problem is the following. We have some polynomial with integer coefficients, degree greater or equal to, positive leading coefficient. What we consider is products of consecutive values of this polynomial, f1 times f2 times and so on up to fm. And the main question is, what can be said about the prime factorization of this? In the simplest case, when you have fx is equal to x, then you just get m factorial. In this case, we have pretty good information about the exponents of primes and the prime factorization. This information together with Stirling's formula can be used, for example, to prove Chebyshev's inequality for the primes counting function pi x. But so what can be said in general when we have some polynomial? So this problem, which I will look at, is also related to the problem of representing primes by polynomials. So there's an old conjecture that if f is some irreducible polynomial with positive leading coefficient, and no prime divides all the values of the polynomial, then f should represent infinitely many primes. The standard example is the polynomial x squared plus 1, for which Hardy and Dillwood formulated the asymptotic conjecture for the number of primes represented by this polynomial. So now assume the conjecture is true and we can represent infinitely many primes. Let's say fm is equal to a prime p. Then when you take the product of f1 up to fm, p, so the prime p will occur only once in this product. Since, from some index m or from some number m onward, the polynomial will be increasing. In particular, for the polynomial x squared plus 1, this is the case. So it's increasing from x equal 1 onward. Okay, so this suggests the following question. Can we prove that if m is sufficiently large, there exists some prime number which occurs only once in the prime factorization of this product of the first m consecutive primes? So in other words, can we show if m is sufficiently large, there exists a prime number p such that the order of p in this product a of m is equal to 1. If we can show that, then this has a simple consequence. In particular, for sufficiently large m, a of m is never a perfect power of any positive integer. The first concrete example of a polynomial of degree greater or equal to was considered by Celeruelo in 2008. He considered the polynomial which I already mentioned, the polynomial x squared plus 1. What he showed was that whenever m is greater than 3, then there exists some prime number such that the order of p in a of m is equal to 1. As a consequence, a of m can never be a perfect power if m is greater than 3. And when we look at the values of the product, the product a of m for m equal 1, 2, and 3, then we see so a of 1 is equal to 2. A of 2 is equal to 2 times 5, which is 10. A of 3 is equal to 100. That's the only case in which we get a perfect power. So this product is equal to a square if m is equal to 3, and otherwise it's never a perfect power. Okay. This work has been extended by various authors. In 2009, Fang extended Celeruelo's work to other quadratic polynomials, 4x squared plus 1 and 2x squared minus 2x plus 1. These are also irreducible polynomials. Then this was further extended in 2011 by Yang, Tokbe, and He to arbitrary irreducible quadratic polynomials. Then, subsequently, many authors considered polynomials of the form x to the k plus 1, where k is an odd number. Note that f is reducible in this case. So the question which we consider does not depend on whether the polynomial f is irreducible or reducible. It makes sense in both cases. Okay, Gürel and Kisezel settled the case k equals 3 in 2010. Then all primes k greater or equal to 5 were settled in 2012. Then, yeah, it makes sense to extend this further to composite numbers. Chen, Gong, and Ren in 2013 considered odd prime powers. Then, later, can you please go? Yeah, okay. Chen and Gong also considered the case when k has at most 2 prime factors. And now finally, in 2019, Day and Leishram, so my collaborator, Palab Day and Chantal Leishram, considered odd case with at most 4 prime factors. So the work which I'm talking about is joined with Palab Day. We consider kind of the orthogonal case when k is a power of 2. So that makes absolutely sense. It's kind of orthogonal to the work that has been done on odd prime powers, and it connects directly with the work of Celeruelo because it's a particular, yeah. So a particular case of that is when we have the polynomial x squared plus 1. Okay, so more in general, we consider products of consecutive values of the polynomial x to the 2n plus 1, x ranging from 1 to m. And we ask what can be said about the prime factorization of this expression. Originally, we hoped that we can recover or we can directly extend the Celeruelo's result, showing that if m is large enough, there exists always a prime, which occurs precisely once in the prime factorization of this product. This turned out to be too hard. So along the lines of Celeruelo's method, we were not able to establish that. But at least we have been able to bound the order of P, where P is any prime, in this product. Our result is as follows. So let n greater or equal to 2 be an integer. So we now consider, not the polynomial x squared plus 1, but all polynomials x to the 2n plus 1, where n is greater or equal to 2. Then we establish the existence of some prime divisor, P, such that the order of P in this product is less or equal n times 2 to the n minus 1. So some expression which depends only on the degree of the polynomial. If, so we can even make that explicit. We can show that if capital M is greater than the maximum of 10 to the 12 and 4 to the n plus 1. So some term depending on n. As a consequence, this product can never be a perfect qth power if q is a positive integer exceeding this n times 2 to the n minus 1. For the special case when n is equal to 2, we have a stronger result. Then we can remove this condition on m, and we can show that for all positive integers m, there exists some prime divisor of this product which has order less or equal 4. Consequently, this product can never be a perfect qth power if q is a positive integer exceeding 4. This is some nice result. So we can never solve the equation, this product, x equals 1 up to m, x to the 2n plus 1, or in this case, x to the 4 plus 1, can never be a perfect fifth power or sixth power, and so on and so forth. Okay, about the method, I have not much time to talk about the method, but it's a mix between analytic number theory, algebraic number theory, and combinatorics. So I have anyway, when I prepared the talk, I have anyway decided to cut the analytic part and the combinatorial part short. Sorry, the analytic part and the algebraic part short. I just tell you the main idea in these parts, and to focus on the combinatorial part. So the combinatorial problem to which everything boils down. Okay, can we go to the slide before this? Yeah, precisely. So
further?
Yeah, so can you please go up?
Up, yes, sir.
Yeah, precisely that slide. Yeah, so the idea is the following, or the key result, which we use in that paper is the following. So assume that a large prime power, p to the n, let's say, divides this product of the first m consecutive values of the polynomial. Then somehow this power will distribute over the factors. That's clear. So therefore, we get congruences of this form, which I give here in 2, in the system of congruences 2. So these factors are of the form xi to the 2n plus 1, where the xi are distinct. And so they have to satisfy congruences of the form, it's congruent 0 modulo p to the k1. So the key point in this paper is, which enables us to extend the Ziller-Aeolus method, that we show that if the sum of k1 up to ks is large enough, then this system of congruences will force the prime number p to be small compared to x1 up to xs. Or more precisely, we can bound p in terms of x1 up to xs. Okay, what is the consequence of that? Yeah, can you go up again, please? Yeah, further up, please. Yeah, so what is the consequence of that? The proof of the main result goes by contradiction. So we assume that m is greater than this number, maximum 2 to the 10 to the 12, 4 to the n plus 1. And we assume that the statement is not satisfied. So that means for all prime numbers p, which occur in the prime factorization of this product, we have that the order of p is greater than n times 2 to the n minus 1. We want to get a contradiction. So then this previous key result about partitions is as a direct consequence that these prime numbers p, which occur in the prime factorization, are bounded in terms of m. Namely, p is less or equal to 2 times m plus 1. Good, so now what is the idea? We consider, yeah, so therefore this product goes just, so when we factorize, when we take the prime factorization of this product, then it's the product over primes less or equal to 2 times m plus 1, p to some power alpha p. And so these alpha p are either 0 or greater than n times 2 to the n minus 1. On the other hand, we also have a simple inequality for this product of the first consecutive values of these polynomials. Namely, so these polynomials are of the form x to the 2n plus 1. Just forget about the 1. Bound these polynomials all by x to the 2 to the n. And take the product. Then you get the m factorial to the 2 to the n. Okay, so now we therefore get an inequality. So we take this product, which is the prime factorization of Pmn, and we can compare this with m factorial to the 2 to the n. We get some inequality, which is the inequality at the bottom of this page. And the idea of Zillow-Aiello's method is to get a contradiction to this inequality. So we show if m is large enough, then this inequality will be wrong. And the key point in this is that these prime numbers p are bounded by 2 times m plus 1. Moreover, to establish a contradiction to this inequality, we need to use, so we need to have some control over the exponents alpha p, which is possible because we can show that a congruence of the form x to the 2n plus 1 congruent 0 modulo p is satisfied. I mean, has a solution only for special primes, namely primes of the form p congruent 1 modulo 2 to the n plus 1. So a solution, so a non-zero alpha p, exists only for a very restricted set of primes. And in addition, we can bound these exponents alpha p because we have some control over the number of solutions of the congruence x to the 2n plus 1 congruent 0 modulo a power p to the j. Okay, so it's possible by such elementary considerations and some analytic results. So in particular, bounds, explicit bounds for the number of primes in an arithmetic progression. So some explicit version of the prime number theorem for arithmetic progressions to get a contradiction to this inequality. Okay, so that's the analytic part, basically. Good, so now the key task is, so first of all, we need to, I need to indicate how to get this key result. This is the algebraic part. So this key result is that the system of congruences, which I stated on the other slide, forces the prime p to be less or equal a certain quantity depending just on the numbers x1 up to xs. So how to get this result? This uses some algebraic number theory. So in fact, for small n's, Palab and I figured out this result by elementary considerations. But for large n, it's much more convenient to consider the problem in the framework of the ring of integers of the splitting field of this polynomial. So we reformulate the whole problem in the splitting field, or in the ring of integers of the splitting field of the polynomial x to the 2n plus 1. And that's a very nice field. That's just the 2 to the n plus 1th cyclotomic field. So we have a lot of information about this field and the structure of the ring of integers in this field. And okay, then using some algebraic number theory, elementary algebraic number theory, we will get some inequality for these prime powers p to the k occurring in these congruences in terms, we compare this with the norm of a certain algebraic integer in the ring of integers of this cyclotomic field. This will allow us to reformulate the whole problem just in combinatorial terms. Okay, so what we can show is the following. Can you go up to the slide with the congruences, please. Okay, so now I need to speed up. Yeah, okay, so this slide, precisely. What we need to find is a number n, depending on little n, such that whenever we have some partition of this number into k1 plus k2 up to ks, and we have a system of congruences, like in 2, then it follows that P can be restricted, P can be bounded in terms of x1 up to xs, basically by the maximum of x1 up to xs. So we want to find a number n, just depending on little n, such that this is satisfied. And using these algebraic considerations, this can be translated into a purely combinatorial problem on partitions. Namely, we want to find the smallest number n, such that whenever we have such a partition, okay, so now you can go down, please. Yeah, this is precisely that. So we can just forget about, or we can remove this condition about congruences. What we need to find is the smallest integer n, such that every partition of n into numbers k1 up to k1 plus k2 up to ks satisfies the following combinatorial condition, purely combinatorial condition. So which compares the position of, the index of kr with kr itself. So for some r, we need that this inequality 3 is satisfied. Then we can deduce that whenever we have such a system of congruences, this P is bounded in terms of x1 up to xs, as stated in that slide. Okay, so this looks a bit strange. So now I don't have much time left. So we actually prove that this smallest number is precisely our n times 2 to the n minus 1 plus 1. And the strategy to prove this is that we construct an extreme partition satisfying this condition. Then from this extreme partition, we deduce that any other partition of the number n times 2 to the n minus 1 plus 1 also satisfies our combinatorial condition. And when we reduce this n by 1, then we can give a partition which does not satisfy our combinatorial condition. So we actually find the smallest number n such that every partition of n satisfies the combinatorial condition. And maybe it's the best thing at the end of this talk just to look at how these extreme partitions look like, because they can be given very explicitly. To this end, you need to go to the next slide. Yeah, so they look like that. So 2, so these are powers of 2. Okay, so these are the numbers n times 2 to the n minus 1 plus 1. And the partitions look like that. 2 is partitioned into 1 plus 1. 5 is partitioned into 3 plus 1 plus 1. So 3 is 2 to the 2 minus 1. So 1, 3, 2 2s. Then 13 is partitioned into 1 7, 1 3, 2 1s, and 1 more 1. Then 33 is partitioned into 15, 1 15, 1 7, 2 3s, 4 1s, and 1 more 1. 81 is partitioned into 31, 1 31, 1 15, 2 7, 4 3s, 8 1s, and 1 more 1. Okay, so you can see a pattern, and you can easily continue this. Okay, so these are the shapes of our extreme partitions, and maybe we go to the last slide. So now we want to show that, in fact, this number, n times 2 to the n minus 1 plus 1, is the smallest positive integer, which satisfies our purely combinatorial condition. And this is very easy to prove. So I have written down the easy proof of that. First of all, n cannot be chosen smaller, because if we just remove one from the partition, then we get a partition which does not satisfy the combinatorial condition. So the way how this extremal partition is constructed. And then to show that any other partition of this number n equal little n times 2 to the n minus 1 plus 1 satisfies the combinatorial condition, we just observe that either the partition has more elements, or at least so at least the same number of elements as the extremal partition, or for some of the summons we have the equation, we have the inequality, so kr prime is greater than kr, where kr is the summand, the half summand of the extremal partition. In both cases, it's very easy to see that the combinatorial condition holds for some index r. Okay. Basically, I'm at the end of my talk. I couldn't say much about the analytic part and the algebraic part, but so at least I could give you some flavor how this problem, interestingly, boils down to a purely combinatorial problem on partitions. Okay, here you see the literature which I mentioned, in particular the work of my collaborator, Pallab Dey and Chandrasekharan. Okay, then we can go to the last slide, which is simply thanking you for your, in this version, I don't have this last slide. It's just thanking you for your attention, for your kind attention.
Thank you, Stephen.
That's all.
Thank you very much. So anyone has any question, kindly unmute and ask.
Stephen?
Yeah.
Yeah, so in your theorem, you said the main theorem where if m is bigger than max of 10 power 12 on 4 power n plus 1, is it because of that combinatorial argument?
Of the what? Because of what?
In one of the main theorem, you said, if m is bigger than maximum of 10 power 12 and 4 to power n plus 1.
Yes.
So is that the one coming from combinatorial arguments, or?
So no, that comes from, in this analytic part, we have to use explicit versions. To get an explicit lower bound for m, we need explicit versions of the prime number theorem in arithmetic progressions, and also related sums of primes over primes in arithmetic progressions of arithmetic functions. So this leads to this concrete lower bound.
I see.
You can also use unexplicit versions with just O constants, and then we don't have any control of a lower bound of m. But we get the qualitative result that for sufficiently large m, this inequality for order p holds for some p.
Yeah, so did you use this work of Bennett and other people?
No. It's purely based on Celoelo's approach. So it's an extension of that, but we have to do much more. We have to, so we get precisely this combinatorial problem in this case.
Good, Shanta. Yeah, good. Stephen, nice talk. Thank you very much.
Yeah, thank you. Sorry for the problem, but
No, not at all. Thank you very much for your talk. Wonderful.
Thank you.
Yeah. So our next speaker is Professor Jaban Meher. Jaban, can you come?
So, can you hear me?
We can hear you, but I can't see.
Sir,
Now
can
you
you
can see?
unmute? Can
No,
you
I
show
have done it. So, now can you see?
No.
Oh. But I have done it. I do not know.
Others, Rishi Babu, are you able to see that?
Sure is here, sir, but Is it
Yeah,
now?
yeah. Now I can see you.
Now, okay, okay. It's taking some time, looks like. So,
Okay. So, Professor Jaban Meher, welcome for today's talk. So he is from NICER Bhubaneswar, and he is an expert in modular forms and cusp forms and things like that. That kind of number theory. So please start your talk. The title of the talk is ModP Modular Forms and Simple Congruences.
yeah,
Please
thank
start.
you very much, Professor Srinivas and the organizers for inviting me for this conference. So let me first share my screen. And can you see the screen?
Yes, sir. It is too small. You can.
Oh, let me do this. Now it's fine.
Yeah, it's better. Yeah.
Yeah. So the title of my talk is ModP modular forms and simple congruences. So we'll define means like first what a modular form is, and then we'll see like what this title means, and then what our work is. So modular form generally begins with the group SL2G. So SL2G consists of all 2 by 2 matrices with integer entries and determinant 1. And we have, of course, complex upper half plane. So the two things we need to define a modular form first. So, but one more thing is that this is why we have defined SL2G and H, because SL2G acts on H by this transformation property or this Mobius thing. So this is the action of SL2G on H, the complex upper half plane. So now we move to the definition of modular form. So a modular form of weight k. So k is non-negative integer, means that we can take here. So a modular form of weight k on the group SL2G is a function from the upper half plane, complex valued function on the upper half plane, such that following conditions are satisfied. So the first property is that the f is a analytic function on H. The second is a kind of transformation property. So f az plus b by cz plus d, that we know that SL2G acts on H. So we have a, B, C, D, and Z. So this is the action az plus b by cz plus d. Each up to this factor cz plus d power k, it is same, means like same f is appearing again up to this factor. And this should be true for any element in SL2G and any element in S. So this is second property. And the third property is that it should have, so this is generally Taylor's expansion, but people say it Fourier expansion. So this is the Fourier expansion of a modular form. So we should have, so these three properties. So modular form of weight k on the group SL2G. So note that I am only considering SL2G here. Later part, although I will not define for other groups, but we'll see actually. So most of our things, means like what I'll talk about is on SL2G. Okay, some part, our work on some other group, that we'll see. So, but this is the actually basic things, means modular forms, whenever somebody starts with SL2G. So that is what I have done. So modular form definition is these three properties. And mostly for number theories, this coefficient. So the coefficients are called Fourier coefficient, AN. So AN are called Fourier coefficients. And for number theories, generally the behaviors of these coefficients are very interesting, and they very nice properties they have, and they have very useful application in many places. So that is why people study from number theory perspective. Means mostly, means like there are other things also people study, but mostly that they study the Fourier coefficients and arithmetic properties, etc. So we'll come to this. So in addition, that if in addition to the above three properties, if the constant coefficient is 0, then we say that this is a Kasper. So although will not come, I mean, like anything to do with Kasper in this talk, but I just define like this. So if the constant coefficient is 0, then we call F a Kasper. So we collect all the modular forms of weight K on SL2G. So this is a finite dimensional vector space. So this is known. And as I said, that for our purpose, the coefficients are mostly important for their arithmetic and then many number theoretic properties. So we denote for and then means like mostly generally A and R in C. So from the definition, you can say that means like the ANs are in C, but they are very interesting when they belong to certain ring or certain field. In particular, some kind of number field if they belong. Okay, so that is what the interesting part for number theorists. So we define for a ring which is a subring of C, we denote by MKR. So MKR means the modular form. We collect all those modular forms such that all the Fourier coefficients are in R. So this is the definition, MKR. So let us see first some examples of modular form. So Eisenstein series for k bigger than equal to 2. So EK, so generally in a first course in modular form, generally you study Eisenstein series, and that is the beginning actually. It's like this is actually the first kind of examples one studies is of Eisenstein series. So Ek for k bigger than equal to 2, Ek is defined like this. So here note that means like here Bk is the kth Bernoulli number, sigma k minus 1, this is the divisor function defined here. So here note that the coefficient, if you see the coefficients, so we are interested in Fourier coefficients. So these Fourier coefficients are rational numbers. So 2k by bk into sigma k minus 1. So this is an integer and this is a rational number. So this is very interesting for us. So we'll come to this also. So this is one first example. And we have the following property that k, I have defined the Eisenstein series for k equal to 2 also, but it is known that for k bigger than equal to 4, this is a modular form. Eisenstein series is a modular form of weight k. Ek is in mk. But for k equal to 2, so this is not a modular form. And this is something called quasi-modular form. It has also some theory and some nice things, but we'll not go to that. But E2 is not a modular form, but for our purpose, for this talk actually, E2 is, and whatever this work, that mod T modular form, etc., E2 plays a very integral part in this theory. So that is why it is very important also. So these are examples of modular form. E2 is something else which is not a modular form. And then one more property is that this so this if we collect all the modular form, this graded ring of all the modular forms, like we of all weights on SL2G. So this is this C E4 E6. So that means it says that any modular form you can write it as polynomial in E4 and E6. Okay, this is again, this is the one property one studies when one studies one goes through a first course in modular form. So let us come to what we want to do. For us, always P is a prime bigger than equal to 5. So sometimes we'll take P equal to 3 also, but that will be mentioned. But mostly we'll be considering P. P means it is a prime bigger than equal to 5. And ZP is the local ring with unique maximal ideal PZP. So this is again one property. One needs to do something more, but so that this if you look at the previous slide, it says that this is CE4E6, but now I am interested in the coefficient, that I am considering the graded ring of MKZP. So I mean, like MKZP means the collecting all the modular forms of weight K, where all the coefficients are in ZP. Then one says, I mean, like one needs to do something to prove that this is ZP E4E6. So that means it says that any modular form with coefficients in ZP can be written as polynomial in E4 and E6 with coefficients in ZP. So this is something else actually. It is not directly follows from the above slide, but one needs to, but it is not difficult. I mean, like one needs to do a little bit to get this result. So why we are interested in ZP? Because as I said that we want coefficients in ZP because so we want to study the congruences of the Fourier coefficients, and then generally we know that congruences means if you take two elements, we study congruences between these two if they are in Z. But similar thing you can do if they are in ZP also. That is why and Z contains ZP. So that is why we are kind of generalizing that in mathematics generally if something is given, so we want to generalize whether how far we can go. So in this case, means like two elements in Z, we study congruences, but similar thing can be done for ZP. So that is why we are studying for ZP also. So now let us define that I have two modular forms. One is weight K, another one is weight K prime. So two different weight modular form. We say that they are congruent modulo P. So I mean like here coefficients are in ZP, and then we say that two modular forms F and G are congruent modulo P if each coefficient, mean like AN is congruent to Bn mod PZP. Okay. So this is the definition that we say that two modular forms are congruent if each coefficients are congruent modulo P ZP. So this is how we define the congruence between two elements in ZP. So let us see some examples first, whether we have examples such that the coefficients are in ZP or not. These are the examples. E2, by the definition, E2, the coefficients are in Z. So in Z, so that is in ZP for any prime. So it is in for P bigger than 5 I am considering. So it is there. And EP minus 1, one checks that, means like one needs to study some congruence properties of Bernoulli numbers to see that EP minus 1 and EP plus 1 all have Fourier coefficients in ZP. So all Fourier coefficients are in ZP. For a fixed, if you fix P bigger than 5, then EP minus 1, EP plus 1 have Fourier coefficients, all Fourier coefficients in ZP. And so this is these are two examples of congruences. So note that let me go to the previous slide. So here you do not need to you can define the congruence. You can define the congruence if you have a Q series of Fourier expansion like this. You do not need F and G to be in modular form. But for our purpose, mostly we'll be dealing with modular form. So that is why we have defined like that. Otherwise, you can study. You can define like this. So here, some examples of congruence. It says that EP minus 1 is congruent to 1 mod P. So EP minus 1 means like this is with P minus 1 modular form. And then 1 is with 0 modular form. So that means it says that from the first example, it says that means like two different weights modular form can be congruent modulo P for some P. I mean, for a certain, I mean, there are examples of two modular forms of different weights such that they are congruent modulo A prime. And the second example is EP plus 1 is congruent to E2 mod P. As I was saying before also, you can define the congruence if they are not modular form also. So E2 is not a modular form, but it says that this is the reason where it plays a very important role, E2. So EP plus 1 is congruent to EP plus 1 congruent to E2 mod P. Okay, so these are two examples, and then like the theory of the mod P modular form, that what is the kind of structure, and then we saw that means like two different weight modular forms are congruent. So whether there is a relation between weights or anything like that for a particular P, etc. So this was first studied by Srinivasan, and he proved the following thing, that if we take two different weight modular form and suppose that they are congruent modulo P, so except for the trivial one means like any of them is not 0 mod P, because you multiply by P to any modular form with coefficient in ZP or means like Z, then it will be again congruent to 0 mod P. Those kind of things we don't want. So if two modular forms are congruent modulo P, then there is a relation between the weights. So it says that the weight are related by that K is congruent to K prime mod P minus 1. So if modular forms are congruent modulo P, then weights are related by mod P minus 1. Okay, so they are in the same equivalence class, mod P minus 1. That is what it says. So this is the beginning point actually. So Srinivasan paper. So this is the lecture, Springer lecture notes. This modular form of one variable. I think part 3. I think. So this is the beginning of what is called mod P modular form, and then this is the beginning of the p-adic modular form, share, and now cage, etc. Many people studied p-adic modular form, cage modular form, etc. So everything, the beginning point is this, because of this this property that two modular forms are congruent, then the weights are related by this. Okay. So, but in that paper, actually, Srinivasan actually proved many more things also. So, for that, actually, in fact, he gave a kind of structure. Structure in the sense that means like here we have two modular forms. We are saying modulo P. Suppose two modular forms are congruent modulo P. Then collect all those, and then means like see whether we get some algebraic structure to that or not. We get any algebraic structure of that or not. So this is what also Srinivasan did in that paper. So let us first define few things, then we'll go to that. So let FP be the field with P elements. So FP be the field with the finite field with P element. And then we have, as I said, that what you do, that modular forms have Fourier expansion like that. That is why we have considered this, that ANQN. So ANQN, so this is natural homomorphism, that ZPQ goes to FPQ. So this is nothing but the AN bar means you modulo PZP you look at, and then you do the reduction. So that is the map. So ANQN goes to AN bar QN. So this is one way. So if you are given Fourier expansion or Q series expansion, people call sometimes, then this is one way of reduction. And then another thing we want to reduce is if one polynomial is given. So I am interested in this work. Only degree, I mean like polynomials of two variables will come. So suppose G is a polynomial of two variables with coefficients in ZP. Then G can be written like this. So then what do I mean by reducing G modulo PZP? So this is the meaning. So if I have G with coefficient CAB, then the reduction of polynomial G modulo PZP is nothing but just you reduce the coefficient modulo PZP. And so this is again in FPXY. Okay. So now, as I said, that you collect all the modular forms and then reduce kind of thing. So collect all the modular forms which coefficients are in ZP, and then reduce modulo PZP, and then look at that what you get. So that this is what our aim that we get some algebraic structure or not. Because when we reduce, even why we are taking all weights, because as we saw from this Swinnerton result that two modular forms of different weights can be congruent modulo P also. So that is why we are collecting all those modular forms, everything together, and then we see. So that is why the first we consider the MZP. It is the all modular forms of all weights with coefficient in ZP, and then we reduce everything. That all modular forms with coefficients are in ZP. Reduce means that we reduce the Fourier coefficients. So what we are getting is that reducing means we are kind of getting the elements are the Fourier expansions, what the coefficients are in FP. Okay, so this is what MFP. So this is MFP. So Swinnerton died. So this is the structure he proved that there is a ring isomorphism between FPXY modulo. So this is the ideal generated by A bar XY. Note that I have defined the reducing a polynomial modulo P. So A bar means here P is fixed. I am considering P is fixed, and then I am looking at what is the structure, that MFP. So if you look at that MFP, I want what is the structure MFP. So they proved that MFP is isomorphic to FPXY modulo the ideal generated by this. And what is AXY? AXY is the polynomial satisfying this. So how this comes? Because EP minus 1, we know that any polynomial is any modular form is a polynomial in E4 and E6. And more, what we know more about it, if the coefficients are in ZP, then we can have the polynomial also can have coefficients in ZP. So that is what AX is, AXY is. That means this polynomial in ZP. Oh, sorry. So the polynomial in ZP XY, the polynomial in ZP XY such that means that if we substitute X E4 and E6, then it gives EP minus 1. So this is what. So they proved this thing, and this is actually the starting point, and they did it for SL2G. So this kind of result has been generalized to modular forms of higher level. So higher level means I'm not giving the definition, but it says that modular forms are on not SL2G, but some subgroups of SL2G. One can define modular forms on subgroups of SL2G. So higher level means people consider congruent subgroup. Generally for number theorist again, means like for because of various arithmetic properties, people consider congruent subgroups. And then congruent subgroup, there is something called level. So if you have SL2G, so people have SL2G result is by Swinnerton there, and then higher level many people have done. So Katz actually did it for gamma n. So gamma n is the principal congruent subgroup, and n is bigger than equal to 3. So he did it for n bigger than equal to 3. And this is the actually beginning of what he did, something called Katz modular form, and periodic modular form actually said it periodic modular form first, and then that was generalized by Katz. And then the method of Katz was means like whatever this Swinnerton did was kind of not too much actually, means like in a elementary way, means like modular form, theory of modular form, etc. they use. But Katz method was using some geometry, algebraic geometry, schemes, etc. he uses. And Gross also did this similar result for the modular forms on gamma 1n, and he did it for n bigger than equal to 4. And its Gross result is also in geometric in nature. So what we have done, so we saw that means like n bigger than equal to 3 and bigger than equal to 4. So nobody has done for n equal to 2. So we thought that whether means like we can do or means like it is too much. So we tried to do for n equal to 2. So this is a joint work with my former PhD student, Sujit Kumar Singh. So we generalized the result for modular forms on gamma 02. So level 2 nobody has done. In fact, we searched many literature and then nobody has done. So we thought possibly whether it can be done or not, and then we are able to do that, and we follow the method of Swinnerton diet. The way we require changes because gamma 02 we have like 2 cusp comes there. Like in SL2G you have only 1 cusp infinity. So all these technical things I don't want to go, but it is not much. Like some modification one needs to do on the method of the Swinnerton diet, and one can prove that this is isomorphic. So here m gamma 02 at p means again I am considering the modular function gamma 02, and this ax is what? So ax is the this thing that in SL2G case we know that the modular form is generated by E4 and E6. So similar thing is there for modular function gamma 02. And the 2 modular forms which we generate are E22 and E42. Okay, so they are also means like in fact they have I think integer coefficients. Okay, so they have integer coefficient. So this says that means like a similar result we have also proved, but here note that the Swinnerton diet result was for p bigger than or equal to 5. So here we include p equal to 3 also, and then for p equal to 3 this changes actually the polynomial changes. So p equal to 3 we have p minus 1. P minus 1 is 2. So we have weight to E22, and then for p bigger than or equal to 5 we have EP minus 1. This is same EP minus 1 as in the previous case. Note that EP minus 1 is a modular form on SL2G. So again, this is a modular form on gamma 02 also. So the same thing. And we follow the method of Swinnerton diet. So next is people have used the mod P theory to study various congruences. And we'll come to that what we have studied. So we begin with the partition function, this congruences by Ramanujan, who gave the congruences. Sorry, anything? Okay, so he gave some congruences that P5n plus 4 is congruent to 0 mod 4, 0 mod 5, P7 and mod 7, and 11 and mod 11. And so, like he didn't give any congruence for other primes. So it was for a long period, it was not known whether for other primes these type of congruences are true or not. And it was in 2003, Algren and Boylan, they proved that there is no other prime for which a congruence of the above form is true for the partition function. Okay, so they proved it. So I think this is invention paper. So they proved, and then they used the theory of modular form mod P. So whatever this Swinnerton diet, and then of course like you have to work with some other, because Swinnerton diet result is only for SL2G, but many other things they use, and then they prove that there is no other prime for which a similar kind of congruences like 5, 7, 11, whatever 13, etc. like that. So for no other prime we get any congruence of this form. So people have used mod P theory to study various congruences. So what is partition function? If you consider the genetic function of partition function, if you look at the genetic function, so this can be considered as a modular form. It has some relation to modular form because this is related to the Dedekind eta function. So that is why like this can be considered as a congruences in modular forms. So this is a modular form, and we are looking at congruences of Pn. So this is congruences in modular form, or Fourier coefficients of modular form. So that is why this is the definition of simple congruence. Simple congruence means any Lorentz series we take may have some negative coefficient also. There is no problem. It's said to have a simple congruence at C mod P if A Pn plus C is congruent to 0 mod P. Okay, so similar thing what we had Ramanujan had for partition function. So similar thing, any Lorentz series of this form, if you take and then you look at whether we said that something is a simple like it has a simple congruence at C mod P if A Pn plus C is congruent to 0 mod P. So this is the definition of simple congruence. So that means so Ramanujan congruences, you can view it. Ramanujan congruences, you can view it as the examples of simple congruences associated to this genetic function or this Lorentz series expansion. So people, as I said, that this can be thought of as the congruences of Fourier expansion of a modular form. So people have tried to see similar kind of things, whether for any other kind of modular form, we get some congruences or not. Like Ramanujan, what he did for partition function. And this was, some examples were studied by Michael Dewar. So he proved that, he proved that this, like here, this kind of expansion, Fourier expansion. So here this kind of means e2 power r, e4 power 6, e6 power t. So this is Fourier expansion, has a simple congruence here, simple congruence if for a prime p, then p has to satisfy this condition. So here r, s, t are integers, not all 0, otherwise it will be 1. So not all 0 and r is non-negative.
Jaban, you can conclude your talk, please.
Yeah, just yeah. So this, I concluded. Okay. So this is.
I didn't mean so fast. Okay.
Yeah. No, like, I'm going. Like you can see the slide also 13 and 12. Okay. So this is what we have done for gamma 02. So similar thing we have seen whether simple congruences, then whether P satisfies this kind of thing or not. So similar result we have proved using our theory of mod P modular form. Michael Dewar proved it because already this SL2G case Swinnerton results, everything was there. So he used it, and we studied the gamma 02 mod P modular forms, and then we gave this result saying that it has simple congruence, then P has to satisfy this condition. Also, we provided examples of simple congruences when this condition is not true. So there are examples when this condition is not true. Okay, thank you.
Thank you very much, Jaban. Any questions, please? Anyone would like to ask? Javan, instead of this AN, I mean, you can take the AN as tau n also. Is it possible?
Like you are saying.
I mean, do you get some, divisibility criteria for tau n from this?
Yeah, one has to see, because here, like we are specifically using those kind of property, but one has to see whether one can get anything. If you look at the results of Michael Dewar also, does it for E2 or E4, E6. So, and then when we take Ramanujan tau means we consider delta function.
Right, yeah.
Delta function means we are kind of looking at linear combination. E4 cube minus E6 square minus E4 cube, something like that.
Yeah.
So this is means, so that I do not know. I think because this is just a monomerial kind of thing they are considering.
Okay, in case there is no questions, so let us thank the speaker for a nice talk, very wonderful talk. Thank you, Mr. Jaban Mehta. Thank you very much.
Thank you.
Yeah. So our next speaker is Professor Padma, R. Padma from VIT. I request her to come online.
So is it Padma Madam available online? I'm just checking, sir.
Yeah, sure. I don't see her online.
Sir, Professor Raghavendra, sir.
Sir, yes, sir.
Whether Padma Madam is available online?
No, sir. Actually, she was there, sir. I think now I could not able to see to her, sir. Even I am searching.
Okay.
Can I call her, sir?
Yes,
Yeah,
I am
please.
calling, sir. I am
Yeah,
calling.
yes, sir. Thank you, sir. One second.
So due to network, Madam has logged out and now again she is joining, sir.
Okay. So Rishi sir, we are running by half an hour late.
Yes, sir, no problem, sir. Because the session will start by 2 p.m.
Okay.
I think it's not a problem. Anyhow, it is online.
Okay,
You can have a lunch and listen the lecture. It's not a problem, sir. Still, Madam has not joined. Madam may be at home today.
Yeah. In fact, she asked me what time is the talk. I told her.
Yeah, Madam joined.
Madam
It
has
seems, sir.
joined. I think Madam joined. Madam?
Okay.
Can you hear me, Srinivas?
Yeah. Nice to see you. So, we were waiting for you.
Hi.
So welcome, Professor Padma from VIT, so the host institute, and she is a very famous cryptographer. She works in number theory and cryptography. So the title of her talk is The Discrete Logarithm Problem over Prime Fields, Non-Canonical Lifts and Logarithmic Derivatives. So you may share your screen, Padma.
Thank you, Srinivas.
Yeah.
First, I would like to thank the local organizers for my colleagues at VIT. To me, IMS reminds me of the IMS library at the Ramanujan Institute for Advanced Study in Mathematics. I was at the Ramanujan Institute as a postdoctoral fellow for 5 years, And during this period, I used the IMS library extensively. The IMS librarian then, Mr. Subramaniam, was kind enough to allow me to use the library, even though I was not a member of IMS. He used to ask me to become a member of the IMS every time I was using the library, but I found the procedure somewhat complicated, so I didn't become a member then. But recently I became a life member of the IMS, and I think I have paid my debt to IMS. I feel honored to give an invited lecture at the Chandrasekharan centenary symposium in number theory. Thanks, Srinivas, for inviting me to give a talk. I never had an opportunity to see or listen to K. Chandrasekharan, but his book on elliptic functions is my favorite. I'd like to recall that I used his paper, which he wrote with Raghavan Narasimhan, titled The Approximate Functional Equation for a Class of Zeta Functions. Srinivas also mentioned this paper in the morning. I used this paper for my PhD thesis.
No, sir, Professor Raghavendra, sir.
Sir,
Some
it seems
problem?
that, disconnected, sir. Madam again.
Okay. I think Madam will join. Hope so.
Network
Sir,
problem
Our
is there.
network also seems to be slow, no?
Yes, sir.
Yes,
Madam,
sir. Sometimes it is breaking, sir. Voice also.
Madam is
because- Yeah, I'm not sure whether my network is slow or the network is slow from other
That's
side.
network only, sir. Because if Raghavendra, sir, can you contact once, Madam?
Sir?
Professor Raghavendra,
Sir. Yes, sir. Yes, sir.
have you contacted, sir?
Yes, sir. Yes, sir. I'm dialing, sir. Madam only. Yes, sir. 1 second, sir. Sir, madam said that she will be joining in few seconds, sir.
Yeah, okay, fine.
Yes, sir. Thank you, sir.
These are the problems with online sometimes.
Yes, sir. Online.
Yes, sir.
If she comes to college, then it will not be a problem, sir. Within the campus, we have a good network. We have not faced any single issue regarding the network, sir. At the campus only, so we don't have any issues, sir. Sometimes if we are sitting at home, we have to depend on other
The campus is working now? It's open?
But not working, sir. Only for faculty, they're asking us to come every alternative day.
Okay.
50% is available on campus at any.
Students are not invited.
And not invited, sir. Students are not there. Only few research scholars are there. They take permission to be in the campus.
IMS is totally shut down. I mean, only admin people are coming sometimes.
Rishi Kumar sir, Padma madam joined, sir.
Padma madam, you can share now. You at home, I think, madam. Madam?
She's muted.
Yes, she's muted.
Padma, you can unmute.
Padma madam, you are muted. Sir, again she left?
Yes, sir, I think. Yes, sir.
Oh. Sir, madam is taking classes online at home.
Yeah.
Maybe very rarely we will get some situation like this. Sir, join here. Now joined. Now joined. Padma madam, please.
Yes, I'm not able to share my screen.
Now it
Yeah,
has
now,
because you have rejoined. So now we have made you as a co-host. Now,
yeah. So let me begin with the definition of discrete logarithm. So if a0 is a primitive root of a odd prime number, which is non-zero mod p, there exists an integer np such that a0 and np is called the discrete logarithm or index of b0 to the base a0 modulo p. And given a0 and b0 modulo p, finding np modulo p minus 1 is called the discrete logarithm problem over the prime field p. Yes, so this is the definition of discrete logarithm.
slide is not moving, but
For example, you take now.
Yeah, yes, ma'am. It is fine, ma'am. Please.
I've got example. Yeah, is it fine?
Yeah, yes, ma'am. It is fine, ma'am. Now.
Padma, you are not audible.
Up to 9 by 2, it jumps around. Okay, the numbers jump around. So it called the finite fields as monkey fields. Okay, because the points jump around when you multiply. So these are used to generate randomness. And one cannot use continuity argument to get the discrete logarithm. Now, the discrete logarithm problem is believed to be computationally difficult if p skip these things is because it is used in internet security standards for symmetric key exchange. Okay. So the Diffie-Hellman key exchange protocol goes like this: a prime number p, which is large, say about 512 bits. Then there are two users, Alice and Bob. They want to generate the same common key for their symmetric encryption. So what they do is the following: Alice chooses a secret number A, and Bob chooses a secret number B, and Alice computes using the public numbers A0 and P, A0 per A mod P, and similarly, Bob generates A0 per B mod P to Bob, and similarly A0. Then Alice and Bob compute the secret key like this. So Alice has the secret key A, and she has received A0 per B mod P from Bob. So she will compute A naught power B power A mod P, which is A naught power AB mod P. Okay. And A naught power A mod P, this is the secret key which he has with him. So he can compute A naught power AB mod P. So they have generated the same common key, which they will use for symmetric encryption. Because A naught power A mod P and A naught power B mod P are sent across an insecure channel, if an eavesdropper comes to know what is A from A naught power A mod P or B from A naught power B mod P, he or she can compute the common key immediately. From A naught power A mod P is discrete logarithm. Same here for A naught power B mod P also. Okay. Now, discrete logarithm problem can be generalized to multiplicative group hyperelliptic curves or affine elliptic curves. So an elliptic curve over a finite field Fp is given by y squared is equal to x cube plus ax plus b mod p, where the discriminant Fourier cube plus 27b squared is not congruent to 0 mod p. And we are choosing p to be bigger than 3. And the set of points on this curve is a finite group under a certain addition law. And it is denoted by E of Fp. Now, if P and Q, P bar and Q bar are points on the curve such that Q bar is equal to n P bar, then n is called the discrete logarithm of Q bar with respect to P bar. And finding n given P and Q is called the elliptic curve discrete logarithm problem. It is, in short, it is ECDL. There are special types of elliptic curves which are called anomalous. When the number of points on the curve modulo P is P itself, then the curve is called anomalous. And these curves should not be used for cryptographic purpose, as Nigel, Smart, Samaev, Sato, and Araki independently found linear time algorithm to compute the discrete logarithm on such curves. So they used two ideas in their paper. One is P bar and Q bar are points on the elliptic curve over a finite field, E of Fp, and lifted to points over Qp, just periodic numbers. Okay. And then they used what is called periodic elliptic logarithm. So the idea goes essentially like this. So if you take P into, if you add Q to itself P times, then because the number of points on the curve is exactly P, PQ will become identity element in the group. Okay. So similarly, P times P will also become identity element. What it means is that if you take elliptic logarithm of these points, it will be a multiple of P. Okay. But the discrete log problem is Q bar is equal to NP bar. So if you take Q minus NP, it will again be a multiple of, if you take logarithm of, not that, because it belongs to even of QP. And if you take P times Q minus NP, then it becomes, the periodic logarithm becomes a multiple of P squared. So now you have an equation like this. So elliptic logarithm of P times Q minus N times elliptic logarithm of p times p is congruent to 0 mod p squared, and n becomes elliptic logarithm of pq divided by elliptic logarithm of p times p mod p. So you have got the discrete logarithm problem. So now comes our attack. We want to see whether smart attack can be used for discrete. Use two tools. One is Teichmuller lift and the other one is Iwasawa logarithm. We use us to use more abstract tools. One is Teichmuller lift. So Teichmuller lift is the following. So by Fermat's little theorem, you have x naught per p minus 1 is 1 plus integer x naught in this set. Q of x naught is called the Fermat quotient of x naught mod p. If you multiply this equation by x naught, then you get x naught. Okay. Now, if you raise both sides to power p minus 1, okay, you will get 1 because of Euler's theorem of congruences. So the Teichmuller x1p is called the Teichmuller expansion of x naught modulo p squared. Okay. The same way one can do x naught power p squared, which is x naught plus x1p plus x2p squared mod p cubed, and this is Teichmuller expansion of x naught modulo p cubed, and if you take power p minus 1, it will become 1 mod p cubed. So one gets a periodic integer which is called Teichmuller representative of x naught, which is got like this. So take x naught per p per k and allow limit k tends to infinity. Now note that t of x naught per p minus 1 is 1 for any x naught not congruent to 0 mod p. One can also think of Teichmuller expansion as Hensel lift. This is periodic Newton-Raphson method. So most of you will know, you would have studied Newton-Raphson method in numerical analysis. So this is Hensel lift is the periodic Newton-Raphson method where you use the polynomial x power p minus x. Now I'll define the Iwasawa logarithm for a periodic integer x, which is x naught plus x1p plus x2p squared, etc., with GCD of x naught comma p equal to 1. The Iwasawa logarithm is defined as 1 by p minus 1 into log x power p minus 1. Now let us see what is log x power p minus 1. You can write this as log of 1 plus epsilon 1p plus epsilon. You can expand this. But note that Iwasawa logarithm of the Teichmuller representative log of t of x is 0. Now let us apply these two tools to discrete logarithm problem or prime fields. So we start with a naught per np congruent to b naught mod p. When you raise both sides to power p, you get a naught plus a1p per np is b naught plus b1p mod p squared. So you have lifted the discrete logarithm problem over mod p to discrete log problem mod p squared. But if you raise both sides to power p minus 1, both sides will become 1. Okay. So you get nothing. Because our aim is to get np. But if you expand the left-hand side here, if you expand expand A naught plus A1P per NP using binomial theorem, P into A naught per NP minus 1 into A1P. But now we know A naught per NP mod P only. Okay. So for doing it mod P squared, we need an extra term which is called carry. So you have A naught per NP is B naught plus beta NP into P mod P squared. Okay. Then if you simplify, you get an equation like this, which is a linear congruence in two unknowns. Here the two unknowns are NP and beta NP. So again, we are in soup. That is, the method fails. So the famous mathematicians Kontsevich and Hans Rizal point out that the difficulty arises because the problem is stated modulo P, but the solution is needed modulo P minus 1. Hence, we convert the discrete log problem mod P to discrete logarithm problem modulo the composite P into P minus 1. So now we consider a special case where the prime P is of the form 2 q plus 1, where q is also a prime number. Okay. This is only for the sake of simplicity and ease of explanation. So now the examples are, you take 11 and 5, 23, 11, 47, 23, and so on. Now, how to convert a discrete logarithm problem modulo P to discrete logarithm problem mod PQ. So let us assume that A naught is a primitive root of both P and Q, and let B naught be relatively prime to Q also. Then the congruence A naught per NP equal to B naught mod P can be extended to A naught per N congruent to B naught mod PQ, if and only if the Legendre symbols B naught by P and B naught by Q are equal. Okay. I'll leave the proof. It is here we use Chinese remainder theorem when the moduli are not relatively prime. So maybe I'll quickly go through the proof. So here A naught per N is congruent to B naught mod PQ if and only if A naught per N is congruent to A naught per NP, which is B naught mod P, and A naught per N is congruent to A naught per NQ, which is congruent to B naught mod Q. And this happens if and only if N is congruent to NP mod P minus 1 and N is congruent to NQ mod Q minus 1. Now notice that P minus 1 and Q minus 1 are not relatively prime. So we cannot use the usual Chinese remainder theorem, but we have to use the Chinese remainder theorem for moduli which are not relatively prime. So the condition is the GCD of P minus NQ. That is the condition. But notice that P minus 1 is 2Q and Q minus 1, okay, Q minus 1 and Q are relatively prime. So the GCD is just 2. Okay. So NP is congruent to NQ mod 2. So next is the Fermat quotient. So when GCD of X and N are relatively, when X and N are relatively prime, X bar phi N, we know by Euler theorem of congruences, it is 1 plus Q of X into N mod N squared. Now this Q of X is called the Fermat quotient of X modulo N. So now we are defining the Fermat quotient for composite numbers. So that is why we have this phi N. It's due to Euler's theorem. So this was defined by Lurch. Fermat quotient satisfies these two properties. If you take product x into y, then Fermat quotient of x into y is q of x plus q of y mod n of x plus zn is q of x. But we want to use Carmichael's function lambda of n. It is defined in the following way. So lambda of 1 is 1, lambda of 2 is 1, lambda of 4 is 2. Prime power, when n is a prime power, it is phi of p per r. When n is 2 per r, it is 2 per r minus 2. So notice that it differs from phi function. And when n is p1 per r1, p2 per r2, etc., pk per rk, then lambda of n is LCM of the lambda of p1 per r1, lambda of p2 per r2, etc. But 2. Now we want the case when n is pq, p squared, q squared, etc. So when p is equal to 2q plus 1, phi of p squared q squared is 2pq squared phi q. Phi q is q minus 1. But lambda of p squared q squared is pq into phi of q. So the order of the group of units modulo p squared q squared is phi of p squared q squared, whereas lambda of p squared q squared is the order of the largest cyclic group modulo p squared q squared. So now we can define capital Q of x by the congruence x per lambda p squared q squared is equal to 1 plus capital Q of x p squared q squared mod pq qq. So now we can do Teichmuller lift for p squared q squared. If a naught per n is b naught mod pq, then the lift is a naught plus a1 pq per n is b naught plus b1 pq mod p squared q squared. Okay. And a1 and b1 are given here in terms of Fermat quotients. Not Fermat quotients, using capital Q. Now the problem with this Teichmuller lifting for p squared q squared is that is because when you talk problem with which we have started, entered it to modulo p squared q squared, but from the way we lifted, if you raise it to power q phi q, it will become 1 mod p squared q cubed. Okay. So again, so we cannot get n this way. And if we use binomial theorem, what happens is we get an equation which is a linear congruence in two unknowns, beta n and n. Okay. Again, we are in soup, we cannot find the value of n. So the carry problem persists in this case also. Okay. So the summary of what I have said so far is the first constraint is because the problem is given mod p and the solution is needed modulo p minus 1, we converted the problem, discrete log problem mod p to discrete log problem mod pq. Okay. But we cannot get n again carry problem persists. Yeah. So if we construct a non-canonical lift modulo p squared q squared, then the problems dissolve. Thus, solving the discrete logarithm problem is a lift. Now, how do we A naught A1, B naught B1, or as in the take A1 plus K into PQ, the whole thing power n is congruent to B naught plus B1 plus L into non-canonical lifts can be written in this form. So here we are adding a term K, the coefficient of PQ, and if K is P for some K1 not congruent to 0 mod Q, then we will have L is equal to L1P for some L1 mod Q. Okay. Now in this case, the order of the group is Q into phi Q. And if you use binomial theorem and expand, then you get by taking A naught plus A1 PQ power n, it becomes B naught plus B1 PQ from what we saw the earlier slide. Okay. Plus
Padma,
the second term n into A naught plus A1 PQ.
Padma.
Yeah.
Your time is up. You may conclude.
Yeah.
You may conclude. Your time is up. Huh? Please.
Yeah, I've finished. This is the. Sure. I have only 2 or 3 slides more.
Yeah. Okay. Yeah, sure.
So if you expand using binomial theorem, you get n congruent to L1 by B naught divided by K1 by A naught mod Q. Okay. Now, if we use the notation dA naught for K1 and dB naught for L1, then n is congruent to dB naught by dA naught by A naught mod PQ. Mod Q as the logarithmic derivative. In other cases where we have, in other case, you get n is congruent to dB naught by B naught by dA naught by A naught mod PQ. In the earlier case, it is dB naught by B naught by dA naught by A naught mod Q, whereas here it becomes, in the more general case, it becomes dB naught by B naught by dA naught by A naught mod PQ. So the canonical extensions of the subgroup generated by A naught mod PQ are labeled by dA naught. So once you get n mod Q, finding n mod P minus 1 is a question of just checking A naught per n and A naught per n plus Q mod P. That will give the correct answer. So one can also think of raising this equation power Q phi Q, and if you raise this congruence, the power Q phi Q, then you get n is congruent to dB naught by B naught by dA naught by A naught mod Q, dA naught by A naught mod P. So this is exactly same as what Smart did in his attack on anomalous curves.
So that I can leave one problem. Last to conclude matram cheyandi sir.
Historically, derivatives of numbers have been studied for a while, and more recently by BO.
It may go up to 2. I accept it, ma'am. Disturb cheyandi.
So when we started working on this problem, the question we asked was this: if A naught power n is V naught, can we write n is equal to some like this? So if you have two functions, f of x and g of x, satisfying the relation f of x power n is equal to g of x, then n is equal to g prime x by gx divided by f prime x by x.
Professor third vachi Professor Jabana Meher.
Which is the logarithmic derivative.
Thank you. And now the plenary talk started in another link.
So I want to acknowledge some of our teachers and friends. Gadia remembers with gratitude being taught advanced topics like the extension of loops in a very simple way by the late Professor ECG Sudarshan. The all-pervasive culture of Bourbaki-style mathematics was imbibed by us thanks to the presence of the late Professor C.S. Seshadri in Chennai. The late Professor K. Ramachandra's philosophy is used in this work. Use elementary methods and analyze the simplest case. We would like to thank Professor M.S. Rangachari, my teacher, who is always encouraging and kind. And I would like to thank my thesis supervisor, Professor R. Balasubramanian, and Professor Bimal Roy, who encouraged academic research in cryptography through the CRSA. And we'd like to thank Professor Ramurthy for encouragement and being very kind to us. And finally, I want to thank my friends Shankaranarayanan, Srinivas, and Arul Lakshmi Narayan for getting relevant papers from the libraries of TIFR, IMSC, and IIT Madras. This work was started at the AUKBC Research Center, where we were before, and brought to this form at VIT. So we thank both the organizations for supporting us. And this talk is based on 2 papers which we published. Thank you.
Thank you, Padma. Professor Padma Gadia. Padma, very nice talk. Unfortunately, due to lack of time, we cannot have questions session. But anyone, if they want a quick question, they can quickly ask.
Sorry, here actually one quick question.
Yeah.
Do you know the proportion of anomalous curves among the elliptic curves over FP? What proportion would it be? Any idea? I think Professor Padma cannot hear maybe. Yeah. Okay. Maybe we'll ask her later. Thank you.
Yeah. Okay, maybe. So thank you, Padma, for a wonderful talk. So I thank you very much. Let's give her a big hand. Padma, you can now close the screen sharing.
Srinivas sir?
Yeah.
Sir, Rishikumar sir has to go start the other session, so he is leaving, sir, right now.
Yeah, okay.
No, it's fine, sir. The session will be continued. Professor Raghavendra will take care. Yes, sir. I will just have 2 o'clock. I have to start another session.
Yeah.
Yes, sir. Thank you, sir. You please continue, sir.
Sir, Srinivas sir?
Yeah.
Any concluding remarks?
Can I say one word, Srinivas, before you begin?
Yeah.
Just that we are very happy that you consented immediately when we proposed this idea of KC conference, KC symposium. Thank you very much for arranging it. And
thank you very much for suggesting this one. This was wonderful, actually.
Yes. Thank you.
Nice.
Please go ahead.
Yeah, thanks. Yeah. So since there is less time, I would like to quickly finish my talk. So this is Hardy's theorem for general functions. So I hope all of you can hear me. Right?
Yes, sir.
So yeah, okay. So in the story starts with Riemann's paper. He has written only one paper in number theory and started what is called analytic number theory from there. Okay, that paper has, started this subject. And in that paper, he defined Riemann zeta function as a function of complex variable, which is analytic in real part of S, which is sigma, to the right of 1. All right. And he derived many analytical properties and stated many conjectures, as you know. And one of the most famous one is Riemann hypothesis. This is $1 million problem. I don't have time to say more on this because everyone knows this problem. All right. So this was in 1859. And since we don't know whether Riemann hypothesis is true or not, therefore one would like to know whether there are infinitely many zeros on the critical line, on the line sigma is equal to half, this one. All right. So one knows that Riemann zeta function has zeros in the critical strip. This is sigma is equal to 0, sigma is equal to 1. And then all complex zeros are here. All real zeros are in the negative real axis, -2, -4, -6, and so therefore, since all the complex zeros are here, and Riemann computed few complex zeros, and he found that they are on the line, on the middle line, this line, sigma is equal to half. And because of functional equation, perhaps he thought that all the complex zeros, they should be on the real line, sigma is equal to half, on the line sigma is equal to half. And that is what is known as Riemann hypothesis. And in 1914, Hardy was the first to show that, in fact, Riemann zeta function has infinitely many zeros on the line sigma is equal to half. And the method of, and then many people started proving Hardy's theorem. In fact, the book of Titchmarsh, it contains several proofs of Hardy's theorem. But the best one, or the easiest one, is given by Hardy and Littlewood. It's a refinement of Hardy's method. And the importance of this method is that it can be adapted to other situations. Okay. That's why this method is extremely important, and my talk is based on this method only. All right. So Hardy and Littlewood, they showed that, in fact, for all sufficiently large t, there is a zero on the half line with ordinate gamma, such that the gamma lies in an interval of the type t to t plus h, with h is equal to t to the power 1/4 plus epsilon. All right. So if you take a sufficiently large real number t, so here is t, then if you go t plus h or t minus h, so in this interval, you will hit a zero of Riemann zeta function. This is on the sigma is equal to half line. All right. And this has led to several refinements, improvements. And in fact, this has led to what is known as exponential sum estimates, exponent pairs and all. Finally, the best known exponent for this h is t to the power 5/32 plus epsilon. Of course, this has been improved 5/32 in few decimal places by choosing best exponent pairs. All right. But roughly, this is the best known. All right. Therefore, this leads to the following questions. Suppose you have an L function of Riemann type, let's say, that means function of finite order, in the sense that, you remove the poles and then suppose the function is of finite order, therefore it has infinitely many zeros in the critical strip. Can one talk about Hardy's theorem for such functions? That means, is Hardy's theorem true for these L functions? And the other question is, suppose you know that there are infinitely many zeros on the half line. Can you say the gap between zeros? This is the local result. All right. That means you take any interval of the type t to t plus h, where t is sufficiently large. Does it contain the ordinate of a zero? That is second question that one is asking. All right. So these are the two problems, and my talk is based on some developments that have happened. Basically, taking Hardy little, how much we can extend it. Okay, that is what. So, in the year 1935, Porter and Titchmarsh, they looked at the function. They took the quadratic binary, a positive definite integral binary quadratic form, qxy, and associated to this qxy to define the zeta function, okay, as rqn by n to the power s, where these rqn's are the number of ways of writing n in this form, in qxy, the number of solutions of n is equal to qxy, all right, in integers. All right. Then Porter and Titchmarsh, they showed that you can take h to be t to the power half plus epsilon. That means in an interval of length t to the power half, around t, you will get an ordinate of the zero of this quadratic zeta function, this zeta function associated to this quadratic form. All right. And in 1995, Shankar Narayanan, he improved this by removing this epsilon. All right. But this half was there for a long time, and it was, it was one of the problems that was supposed to be difficult. And meanwhile, Jutila developed something called transformation techniques, where a sum, an exponential sum, is transformed into another exponential sum, which is easy to estimate. And he used it for cusp-form L functions and proved many good results. And me along with him, we managed to cross this half line, this half exponent half, to come to the left of half. So we were able to prove that this is t to the power 5/11 plus epsilon. All right. And later, with Stephen Bayer and Usha Sangle, we improved it further to 3/7. Remember, 3/7 is smaller than 5/11. And it's possible to improve it further, but I think we have got bored and we left it here. All right. So this is the best known as far as the local results are concerned. Local results means the gaps. That means at an interval of h, is there a zero? All right. And now comes a classical paper of K. Chandrasekharan and Raghavan Narasimhan. And in fact, this is the paper which I studied during my master's and MPhil, and which has perhaps motivated me to undertake analytic number theory. All right. So there, they looked at this quadratic, take a quadratic number field and look at an ideal class in the number field K. Okay. If the class number of K is bigger than 1, then there are several ideal classes. Now take an ideal class C and look at the zeta function associated to that ideal class. So this looks like summation 1 by norm of a to the power s, where a runs over the ideal C, the non-zero ideals. All right. So this is the ideal class zeta function. And Bruce Pernd, he, in 1971, he showed that, in fact, you can take h to be t to the power half plus epsilon. This holds. Shankar Narayan, in the same paper that I mentioned before, he managed to remove this epsilon and replace it by log t. All right. Okay, and the paper, our paper by this paper, in fact, this holds true for ideal class zeta function of an imaginary quadratic field, because there is a one-to-one correspondence between ideal classes in an imaginary quadratic number field and the positive definite integral binary quadratic form. Therefore, our theorem gives you better exponent for ideal class zeta function. All right. And therefore, how far we can, extend this Hardy's theorem? So recently, with Jaban Meher and Sudeep Pujari, we looked at L functions associated to half integral modular forms. These are FNs are A and Q to the power n. You have seen in the morning in Jaban's talk. So assume that all the Fourier coefficients are real, either all real or purely imaginary. These are required for technical reasons, so that a certain function is real. Then the L function attached to F has infinitely many zeros on the critical line. So the problems are different. I mean, it doesn't, Hardy's method doesn't straightforward generalize to these things. There are technical difficulties, but if you can avoid those, if you can patch those technical difficulties, then you get a theorem. All right. And in fact, they have done much better than this. They have also studied local results for this function. So another thing I would like to mention is Marty Jutila in 1984, he considered this cusp form L functions. The L function associated to a cusp form F of weight K for the full modular group. And suppose that ANs are real for all n, then H is equal to T to the power 1 by 3 plus epsilon holds. So a very good result, because from half he went to 1/3. All right. And this is where he developed the transformation techniques that I was mentioning before. Okay, it's a very, very, very important paper. All right. And currently, like, we are able to show that if you look at, if you take a non-abelian cubic field and look at the Artin-L function associated to K, which is given by the Dedekind zeta function divided by zeta Riemann zeta function. This is the Artin-L function associated to K. Okay. And we are able to prove that we can adapt the method of Jutila here and show that H is equal to T to the power 1/3 plus epsilon. And in fact, this improves the result of Weinstein, who showed that T to the power half plus epsilon holds. All right. So this is in the stage of writing, this is being written down right now. So let me quickly go through some slides on what is the basic method and where is the main problem comes. Hardy's method says that suppose you have a real valued function and suppose a continuously differentiable function, and suppose it doesn't vanish in the interval AB, then the mod of this function, the integral or the integral of the mod, will be same. This is elementary fact. As a result of this, if this is not true, if the equality is not true, then it implies that fx changes sign somewhere in between A and B, which means that fx has a 0 of odd order in AB. That's the basic idea. And now everything reduces to, if you want to show a 0 of this one, you have to get hold of a real valued function. That follows from the functional equation that Riemann zeta function satisfies. Riemann zeta function satisfies a functional equation of this type, which can be written as zeta s is equal to chi s zeta 1 minus s, and this chi of half plus it in absolute value is 1. With this information from the functional equation, you form this function zt. And because of functional equation, zt is real for real values of t. Not only that, since chi of half plus it is absolute value, in absolute value it is 1, therefore mod of zt is equal to mod of z of half plus it. And hence, the zeros of zt coincide with the zeros of zeta s on the critical line. Therefore, one can use the previous idea, the elementary idea. Therefore, you assume that Zs has finitely many zeros or no zeros. And in that case, you can take a large real number t, so that between t to 2t, there is no zero of the zeta of zt. So for local results, you replace t with t to t plus h. This is the only difference. Okay, here. All right. So one now has to estimate this one and estimate this one and show if there is a violation somewhere, if the equality is violated. All right. So what one does is one finds a lower bound for this function. It's easy to find a lower bound, and then one finds an upper bound for this side, and then compare both the things. If there is a violation of equality, then it shows that there is a zero between t to 2t or t to t plus h. That's the basic idea. All right. So as it happens that one of the steps is easy. Lower bound estimation is pretty easy, straightforward. All right. I will not show all these things. So lower bound results are pretty easy. Straightforward from the function, manipulate the function and show that in fact t to tt, zt dt in absolute value is at least some constant times t. Okay, this constant is absolute. All right, and therefore, if we can show that the upper bound is uniformly bounded by t to the power alpha for some alpha less than 1, then the equality is violated and we establish the theorem. All right. So therefore, what one does is one looks at this function and transforms it by by a change of variable. You have this function now. Okay, now uses Cauchy's theorem and all these things to estimate an upper bound for this function. So this integral is like this. So standard ways are like we are on the line sigma is equal to half plus it here. Sigma is equal to half plus it. So either you move the line of integration to the right of sigma is equal to 1, where this zeta function is analytic, or you stay on the half line and use a formula, approximate formula for Riemann zeta function, because you cannot use the series representation of zeta s on the half line. It's not valid. So these are the two standard ways classically one does, and shows that in fact, if you want to remain on the half line, you use this approximate function equation. All right, which is not a easy one. All right. Anyway, recently, Usha noted that, in fact, you don't need to use approximate functional equation. In fact, the first approximation to Riemann zeta function itself is enough to prove Hardy's theorem. And that is there in the recent paper of her. All right. So using all these things, one can show that the lower bound is bounded by a to the power a times t, whereas the upper bound is bounded by t to the power alpha. So while doing the upper bound estimation, this is the crucial sum that one needs to estimate. One should show that this is small in certain sense. All right. In all the problems that one deals, this is the kind of sum that one encounters. And if you can show that this is small in a certain sense, then you have a Hardy's theorem or the local gap theorem. That means you will find an H. All right. But this is the most difficult part. All right. In order to estimate that, one has to use exponential sum techniques, which I'm not going to explain here. So ultimately, what one gets is the upper bound is bounded by, for Riemann zeta function, t to the power 3 by 4. Okay, and therefore this leads to a contradiction of the equality, and therefore there is a t for which there is a 0, and since this capital T is arbitrary, this shows that there are infinitely many zeros. Now, what Hardy Littlewood did, they looked at this t plus h, and they showed that this is in fact little o of h. Whenever h is t to the power 1 by 4 plus epsilon. All right, and therefore they got their result. All right. Okay, these are the basic. So therefore, what is the main point? The main point is reduce the upper bound estimation to evaluation of certain exponential sums. Then show that these exponential sums are small to arrive at a contradiction. For example, in the case of Chandrasekharan and Narasimhan, for ideal class zeta function, they reduced the problem to showing that this exponential sum is small, little of t, as t tends to infinity. And by using the arithmetic nature of ANs, because they essentially count lattice points inside certain bounded region, they could show that this is little of t. And therefore, they got Hardy's theorem for ideal class zeta function. Very recently, for degree 2 L functions in the Selberg class, I will not define here Selberg class. It's a class of functions having properties which are similar to Riemann zeta function. All right, and there is a degree associated with every function. And one of the big conjecture is classify all the functions of a given degree. Another conjecture is show that the degree is a positive integer. We don't know this. Classification of all functions of degree 1 in the Selberg class is done. There are only Riemann zeta function and Dirichlet L functions. We don't know all the functions of degree 2, but we know many examples. For example, zeta square is in degree 2. A product of a Riemann zeta function and a Dirichlet L function is in degree 2. L functions of a cusp form, they are in degree 2, and all these things. All right. So the degrees are defined in terms of the functional equation. So what we managed to show with Anirban and Krishnan Rajiv Kumar, that for you take any degree 2 function, and if you assume this condition, which is not we are not asking for too much, all the functions that we have, they satisfy these things, then Fs has infinitely many zeros on the critical line. So this is the only result known for Selberg class of functions of degree 2. We don't know any example, any proof for if the degree is bigger than 2. All right, because the upper bound estimation is very, very difficult. For the half integral weight, this is the crucial sum that comes up after you manage to show everything else is all right, and one needs to show that this is small in this sense. And this is done by using a theorem of Iwaniak. All right, I think I will stop it here because it is 2 o'clock already. I have few more transparencies actually, but I don't want to flash it. So the point I was trying to make is, the things that was derived by Hardy Littlewood, the proof, the way they have analyzed the problem, it's amenable to extensions, and still people are working on that, and it is giving important results, new results in this theory of zeta functions. So I think I will stop it here. Thank you very much for your kind attention. In case if you have any questions, please feel free to ask.
Yeah, I have one question.
Yeah.
So you mentioned the gaps for the ideal class zeta functions for quadratic fields.
Yeah.
Is there any hope to break the 1/2 exponent here in that case?
For the indefinite forms?
Yeah, right.
For the indefinite forms, yes, there is. I mean, we don't know actually how to compute, that sum that we have. I mean, we need to show that, this an e to the power 2 pi I n alpha for every rational alpha, n less than or equal to capital N. This is little o of n. And for indefinite forms, counting these lattice points becomes little difficult because the region is unbounded. But if it is, if one can devise a method.
Yeah.
Yeah, any more questions?
I couldn't hear at the end, but okay. Yeah, so one needs some ugly regions then.
So I was saying that, could you hear my answer? No. Stefan?
Yeah. Yes.
So
no,
I'm
I
saying
couldn't.
that,
I couldn't hear the rest of your the end of your answer.
Yeah. So I was saying that, if there is a way of computing this, this lattice points, the number of lattice points inside a bounded region, inside this unbounded region, because the region is unbounded, we don't know how to count it. All right. So this becomes infinite, and that is the trouble. But it should be possible by some clever means. It should be possible.
It's probably inside some, bounded by some hyperbola region.
Yeah.
Yes. Yeah. Okay. Yes. Okay. Thank you.
Yeah.
Srinivas, one small question. When you talked about things like L function corresponding to imaginary quadratic field, does it give this kind of information like what is the smallest quadratic non-residue, things like that? Would it analytic information give this kind of information also? Because L function will involve quadratic symbol, right?
Well, the quadratic non-residue, the least positive, you mean primitive root type of thing, right? I mean,
yes.
That is, L functions comes into play there, all right. But I don't know these kind of estimates whether they're useful or not.
I see.
For example, if one assumes, the zero-free reason. For example, if you assume the zero-free reason, Riemann hypothesis, for example. Of course, for these things, Riemann hypothesis is not true, because if the class number is more than 1, then there are zeros beyond the line half. In fact, even to the right of 1, there are zeros.
Right.
All right. In any case, they have infinitely many zeros on the half line. And if one assumes not for this, but GRH in general, for primitive L functions, then one can show that the primitive root can be computed quite easily. That means in a log p square time, you have a primitive root. So for that, the L functions associated to primitive, quadratic, primitive characters, they are useful. I don't think these are useful. Yeah, because they have zeros outside the line half.
Okay. Thank you. And one small question about what is the record now about the number of zeros on the critical line? Any or proportion?
This is record is about 41%.
I see.
Yeah, I don't remember exactly the recent, by several people they have done it.
Okay.
But yeah,
just for curiosity.
1/3 and 2/5 was the older one. 1/3 by Conry and Bosch, and then 2/5 by Levinson. And recently, it has been improved.
And since you are
but nowhere near 50%.
Okay, since I'm asking these questions, I might as well ask one more question which I have no idea about. Siegel zeros, anything known about them now?
No.
Okay.
We don't.
Okay. Okay, thank you very much.
Yeah, thank you.
Nice talk.
I think I can stop my sharing.
Please. Thank you. Nice talk.
Yeah, thank you very much.
Sir?
So shall we call it a day?
Yes, sir.
Then, I mean, as far as symposium is concerned. So I really would like to thank all the speakers in the number theory symposium for kindly accepting, the invitation and giving a wonderful talk and making it a success. And this is really a good tribute. And I really thank Professor Suri and Professor Piyush for coming out with this idea, because, I mean, if you would not have done, then it would have been injustice. So thank you very much, and have a good time. Stay safe. Thank you very much.
Yes, sir. Thank you so much, sir. On behalf of IMS 2020 and Organizing Institute VIT, I would like to thank Professor Srinivas sir for conducting the Chandrasekharan Centenary Symposium on number theory. And also we would like to thank the speakers, Shanta Laishrams, Stephen Baer, and Jeban Meher, and Padma Madam. Yes, sir. Thank you for a wonderful symposium.
Thank you. So I'm leaving, huh?
Yes, sir. Okay, sir. Well done.
Bye, Srinivas.
Okay, thank you. It was really nice talk.
Bye.
Thank you.
Okay, professors, we will be ending the meeting. Okay, we would like to invite you for the next session for 2 o'clock.